welcome to this session on fault diagnosis and fault tolerant control for safety of marine systems. I am Christophe Berenguer from Grenoble University in France, and I will have the pleasure to co-chair this session with Reza Shahani from Rostock University, Germany. This session is an invited session, and it has been organized by Vassorepa, Blanque Morgens, and Andrea Monterio. And we will have 6 presentations this morning. And we will start by a first presentation given by Abhishek Dayani from Delft University. So please, Abhishek, the floor is yours.
Good morning, everyone. My name is Abhishek Dayani, and I'm going to present the first presentation. This is work I did along with my supervisors from TU Delft, Rudy Nechenborn and Vassorepa, and it's titled A Multiple Sensor Fault Diagnosis Scheme for Autonomous Surface Vessels. So these are the contents of my slide. I will start by introducing the problem to you first. And so ensuring safety in maritime domain, it has been an open challenge for a long time. And even though there are strict rules and regulations for navigation, for collision avoidance, accidents like these two happen all the time. And these are just 2 examples from the last decade of accidents that led to not just casualties, but also huge economic losses. On the left, you see the case of the container vessel Ever Given, which was grounded in the Suez Canal in 2021. On the right side, there is the very recent case of the container ship colliding with the Francis Scott Key Bridge in the US. Now, there are many reasons given for such accidents to happen. Sometimes it's bad weather conditions, negligence on the part of the crew, or loss of power of the ship. And if we look specifically at the numbers, and this is from a report from 2022 from the European Maritime Safety Agency, and according to this, collision, contact, and grounding or stranding of the vessel, which can be put under the umbrella of navigational casualties, represent 43% of all casualty events that are reported in the European Union in the year 2022. So that makes a good case for autonomous vessels, because autonomous vessels will have improved navigational capabilities. But there is a caveat to that, and that is best explained with this Trojan horse analogy, which is to say that maritime industry looks at autonomous vessels as an alternative which is safer. But at the same time, there are new risks that are introduced because there are new components on board, specifically the sensors on board. And faults are like these hidden soldiers within this Trojan horse that can further jeopardize the safety of the system. So that is one of the main motivation, and that is where fault diagnosis comes into play. And to explain it very simply, when we have a vessel with no fault diagnosis capability, and here I'm talking specifically about sensor faults, then no action is taken and it leads to a failure. On the other hand, with fault diagnosis and fault tolerant control algorithms, when a sensor fault occurs, these FDI algorithms can send an alarm to alert the human operator. For higher levels of autonomy, we can move one step further and we can say fault tolerant control algorithms can accommodate for these faults. They can reconfigure the controller so that we can obtain newer operating conditions and we do not have to stop the current operation. Now, moving towards the problem formulation and focusing on the system, which is autonomous vessels. Now, one of the things that we found during the literature review on this area was that most of the research focused on either single sensor faults, or if they considered multiple sensor faults, they would consider structural or simpler kinematic models for these autonomous vessels. But in our opinion, especially for maritime applications, the external disturbances impacting the vessel must be considered if we are trying to improve the detectability of fault diagnosis. And that is why we opted for this 3 degree of freedom hydrodynamic model of the vessel. Here the states are the position, the heading, and the velocity of the vessel. And then we also modeled the impact of external forces such as wind and other unknown external forces acting on the vessel. We also modeled the navigational sensors which are typically found in these kind of systems. GPS for measuring the position, accelerometer for velocity, and gyro compass for heading, and we use simple linear measurement models to represent these sensors. Now moving towards the proposed methodology for sensor fault diagnosis. The overall methodology can be summarized in this diagram over here. So the first thing that we do is we take all the sensors that we are interested in and we decompose them into these separate sensor sets. This will allow us to improve fault isolability, as we will see later on. And for each of these sensor sets, we have a separate sensor monitoring module, which consists of observers. So we use observers. It's a model-based method, and we use observers for residual generation. And then there is a fault detector, which uses these residues to detect the fault and produce this signal called the detection vector, and then it is combined, all of it, in this aggregator module, and the aggregator module finally provides us with the diagnosis set, which consists of all the potential sensor faults that have occurred. So let's go step by step, starting with the sensor monitoring modules, and more specifically the observers. So we designed the observers in a way that we can obtain structured fault sensitivity, which means that each of the observer is designed to be insensitive to the certain sensor measurements. So in this case, the observer 1 is insensitive to the sensor measurements of velocity, and the observer 2 is insensitive to the measurements in position. And by doing that, we will obtain fault isolation, which is improved from the general case where there is a single observer used. Moving forward, now that we have the observers, we will use this observer for residual generation purpose in this fault detector module that you see. So this residue is simply defined as the difference between the sensor measurements and the state estimate that we obtain from the observers. And under healthy conditions, that is to say that there is no fault, we can find out bound on this residual in terms of the bound on the state estimation error and the bound on the sensor noise. And we make an assumption here that we know the bound on the sensor noise. Now, using these equations and using the equations for the state estimate error, we derive an adaptive threshold, which is represented in this little bit complicated looking equation. And this is an adaptive threshold, which means, well, there are a few points to note. One, because we can write down this equation explicitly, it also means that the state estimation error is bounded, and this adaptive threshold is actually a bound on that state estimation error. Secondly, it's an adaptive threshold, which means that all the bounds, whether it's the bound on the sensor noise as well as the bounds on the unknown uncertainties, are incorporated into deriving this adaptive threshold, which means that we can guarantee that no false alarms occur. And finally, although this equation looks pretty complicated, it can actually be implemented using linear filters. So that is a great advantage in my opinion. So once we have these adaptive thresholds, we get these decisions which are computed whenever by using the residual signals and the thresholds. And then we finally go to the aggregator module. So the aggregator module takes in all these decisions, combines it into this decision vector, and then we compare this decision vector with the sensor fault signature matrix, in which Each column represents a possible set of occurring combination of faults, and each row represents the analytical redundancy relation. So whenever we see a 1 in this table, it means that that combination of fault can lead to the violation of the particular analytical redundancy relation. And 0 means the opposite. So we also have an asterisk in some places in this table, which means that there may be a possibility that the combination of faults can lead to the violation of that particular analytical redundancy relation. So in that way, we are using the sensitivity of these residuals into account for the purpose of fault isolation. So now to validate this algorithm, I will present to you a simulation example. And for the simulation case study, we use this vessel. It's called Tito Neri. It's developed in our lab, that is the Research Lab Autonomous Shipping at TU Delft. It's a model scale vessel. It's around 1 meters in length, around 30 centimeters wide, 17 kilograms. And it is equipped with GPS, IMU, gyro compass, and also some other advanced sensors, but we focus on these. And then we create a fault scenario. Fault can be represented by this equation on the left side. In this particular scenario, we consider permanent, consistent faults that occur at, so there are multiple faults, one affecting the gyro compass sensor and one affecting the GPS or GNSS sensor at times 500 seconds and 1500 seconds respectively. So this is how the simulation goes. So in each of these plots, the blue line represents the residual signal, the green line is the adaptive threshold, and the red line is the decision logic, which goes to, it's a binary variable, it goes to 1 as soon as the residual crosses the adaptive threshold. And this is the monitoring module 1. You see that the decision logic goes to 1 at time 1500 seconds. So we get our first decision variable, and then the monitoring module 2, and finally the monitoring module 3. So this is the one which corresponds to the velocity measurements. There are no faults in the velocity measurements, so you see that the violation of the adaptive threshold does not happen here, and decision line remains at 0. And as a result, we get this finally the diagnosis set, which correctly isolates the combination of faults that have occurred. So in that way, to conclude, in this presentation, I showed to you a model-based sensor fault diagnosis scheme that is capable of isolating multiple sensor faults affecting autonomous surface vessels. One of the contributions of this work is also that we derive adaptive thresholds to ensure that no false alarms occur. To extend this work further, we plan to extend this to applications involving multiple vessels cooperating together, and then also focus on the fault identification and fault-tolerant predictive control to take it one step further, and finally to use improved models for vessel as well as estimation of the external disturbances so that we can improve the detectability and overall performance of our FDI algorithms. So that's the end of my presentation. I would like to invite you to check out our website for our research group, and thank you for your attention.
Thank you for your presentation. We have time for comments, feedback, questions. Yes.
Thank you for a very nice presentation. And you kept time and therefore gave a brief presentation. So I would like to invite you to comment a little bit more on, you said rightly that you use the signature matrix to isolate your faults. You also have an estimator that uses the same sensors to estimate the state. And perhaps you would comment a little bit before on how to prevent your state estimator from being affected by the faults in sensors while you are estimating online. My name is Måns Blanke, by the way.
So if I understood correctly, the question is how do we ensure that the estimators do not get affected by sensor faults? So for that purpose, yes, I will go back to this slide. So yes, the way that we design these observers is, so there is certain difference in the way we design these observers. We are trying to use estimations for positions and velocities, which are related in some sense analytically, to create these observers and ensure that these observers do not use the measurements for the corresponding case, so for the corresponding sensor that is impacted by fault. So you can think of this as a generalized observer-based scheme where we try to create a bank of observers and ensure that each observer is not affected by certain measurements. And that's the methodology behind the observer design.
Have you had any sorts of the multiple faults? Because that's the next.
Yes. Yeah, so that was another issue that came up when we were designing these, is that combination of faults can, when we are trying to look at multiple faults, for that we also utilized another interesting fact, and that is to say that some faults, even though they appear in these models and impact on other measurements, the sensitivity of those faults is limited. And that's why you see that we put also these asterisks in these columns of the fault signature matrix. And that basically tells us that there may be a possibility that that fault is impacting causing the violation of the analytical redundancy relation, but the chances are low, or we might consider it as the last option. Yeah. Hope that answers your question.
Thank you for presentation. How do you select the threshold adaptively? How do you select adaptive threshold adaptively?
So these adaptive thresholds, we design them. So one of the assumptions on which we base these adaptive thresholds is that although there are uncertainties, and uncertainties as in the forces that affect the vessel from outside, and also uncertainties because of sensor noise, we assume that we know certain bounds to these uncertainties. And in the process of deriving these, we include those bounds in the solution to this the residual bound. And in that sense, when there are certain uncertainties that impact the vessel, their impact is also observed in these the bounds, and that's why these are adaptive.
Thank you for your presentation. What is the output of your system?
So the output is that diagnosis set, which is the set of all possible combination of faults that have affected the sensors. So at the top, you see the script DS, that's the final output. Yes.
Okay, we have time for one last question. No? No more question? So thank you. The next presentation is given by Reza Shahani from Rostock University. So please, Reza, the floor is yours.
Okay. Good morning, everybody, and thank you for attending to this session, and welcome. The presentation here is the ESO-based fault-tolerant funnel heading control of surface vessels. It's a cooperating work with Martin Korowski, Nick Eisenblätter, and Thorsten Jansch from Institute of Automation, University of Rostock. The problem is here about heading control, and heading control, as we know, it's a crucial factor in every navigation system, and because of that, a lot of controllers, for example, H-infinity control, sliding control, adaptive control, predictive control, and intelligent control proposed for this purpose. We have a lot of problems from the control point of view for this heading control, but some of the most important ones are one of them is actuator faults. We have actuator faults in our heading control, for example, for rudder, and these actuator faults can be loss of effectiveness, can be bias. The other one is that usually some ships are equipped just with a sensor to measure heading, but we need sometimes heading rate in our control purpose, and so we have to deal with that. And the other one is most methods usually focused on a steady-state performance. Steady-state performance is important, but we should also focus on transient performance too. Transient performance is as important as the steady-state performance. And last but not least is the environment of the ships. We are dealing with a lot of disturbances like wave, wind, and ocean currents. Okay, what we have to do? First of all, for problem formulation, we use a simple model for the, it is called a Nomoto model. That in this simple model, x1 is psi, is the heading angle, x2 is psi, that is the heading rate, and k and t are respectively low frequency gain and time constant. Delta W represents our external forces, can be ocean currents, can be wind, but here we just consider low frequency wave that has a reason. If we have time, we can talk about it later. And about the actuator fault, we consider actuator fault in this way, as by this equation. And this equation, in this equation, delta is the designed rudder command, and sigma f and bf are formulated in this way, that sigma bar is an unknown continuous function, belongs to this set, and F bar is also an unknown continuous function. Tf is the time that fault occurs, and the T function is formulated in this way. This formulation has some advantages. First of all, by considering alpha, we can somehow model abrupt and incipient faults, cases that we may have. The other one is that when we consider this function, this sigma f and bf becomes continuous function, which is very important because when we want to design extended state observer, this is very crucial because most of the time we are assumed that they are, let's say, continuous, but most of the time this may not happen when we have abrupt changes. And by this formulation, we have these cases. If sigma f equal to 0, bf equal to 0, we have fault-free case. If sigma f is between -1 and 0, and bf is equal to 0, then we have rudder loss of effectiveness. And if sigma f equal to 0 and bf is not 0, we have rudder bias. Okay. Now, for our problem, what we do, we gather all the terms that are uncertain related to the environmental disturbances and also fault to a term called X3, to the term X3, and this X3 is formulated in this way. It is called total disturbance. We want to somehow estimate this X3 with extended state observer. What we assume that our heading angle is, belongs to this set. It's a somehow normal, it's a somehow very logical assumption, and we assume that this X3, which we assume in this way, and its derivative is also bounded. It is also logical because we have limited resources for producing energy in our physical systems. Okay, but what we are dealing for our control objectives, the first one is that we want to estimate, as I mentioned, the total disturbance. The total disturbance caused by the rudder faults and the environmental disturbances. And at the same time, we want to estimate the heading rate. So we have to do it simultaneously. So we propose an extended state observer in this way, and omega 0 is a design constant. It's a simple extended state observer, and we can use it to estimate the total disturbance and the heading rate simultaneously. This is the first objective. The second objective is we want to confine that, as I mentioned, transient performance is also important. We want to confine our error, this one, the tracking error of the heading angle, in a shape like a funnel. This FV1 and minus FV1 is chosen in a way that we reach to a desirable transient and steady state performance. This comes from the funnel theory, and in order to do that, we propose this funnel error surface. And this funnel error surface is the best one proposed recently, and in comparison to the other funnel error surfaces, it doesn't have the drawbacks because other funnel error surfaces may have the differentiability problem, may have limit our initial condition and so on, but this doesn't have this problem. And by proposing this, we propose this virtual control, and the gain here is a constant gain, and it's a positive constant gain. And also we use the dynamic surface control theory, which is very important when we are dealing with complexity of calculation, and we have a lot of, and if we want to find the derivative of the virtual control, we use this dynamic surface control theory to avoid that complexity of calculation. And the other objective that we are dealing in this, let's say, paper, we want to confine the tracking of the filtered virtual control, which is defined by this equation, Z2 equal to X2 hat minus V bar, to some funnel boundaries. Again, we propose for this purpose the funnel error surface in this way, and the FV2, the parameters of the FV2 is designed in a way to satisfy the transient and steady state performances. And finally, by these objectives, we come to this actual control or rudder command, and the gain is chosen positive constant. And by this actual control and let's say the virtual control, we come to this theorem that for any bounded initial conditions, if we consider any bounded initial condition, and these two conditions that from the beginning of our the initial condition of Z1 and Z2 are confined to the funnel boundaries, then we can prove that all the closed-loop signal are semi-globally uniformly ultimately bounded, and Z1 and Z2 will remain in the prescribed boundaries for all time. That is the theorem that we proved it mathematically. And for simulation, we consider a Mariner class vessel with these parameters, with a normal Mariner class vessel that has been used for a lot of papers. And for modeling the environmental forces caused by wind, currents, and low-frequency waves, we consider this simple model that V of t is zero mean Gaussian white noise. And for the fault, we consider both bias and loss of effectiveness. It happens at t equal to 200 seconds. And the alpha is considered 0.5 to consider somehow abrupt and incipient fault together. And for desired heading, we consider this model reference guarantee that assumption 1 is satisfied because it guarantees that all the trajectories are bounded. And the control parameters are chosen in by this table for our desired performance. And then we come to this, let's say, figure. And we see that X1 tracks phi d very perfectly and without any somehow very small error. And Z1 is always confined in the or to the funnel boundaries in a perfect way. And also X2 tracks the desired phi or C or psi d dot, or the desired trajectory for the heading rate by this shape. And we can see that Z2, which is X2 hat minus V bar, is confined in the related funnel boundaries. And we see that X1, the estimated of X1 is perfectly done, and with somehow in a very perfect way this has been accomplished. And the estimation of X2 with some small errors also has been done in a perfect way, so we can ignore that. And in order to compare the estimation of total disturbance, we depicted Tk x3 and T over k x3 and T over k x3 hat to compare it with the rudder angle. And we see that our rudder angle is somehow in the range of the total disturbance. And we see that first of all, the estimation is done very well, and rudder motion perfectly to somehow reject this total disturbance. And if I want to conclude, we just propose an ESO-based fault-tolerant funnel heading control for surface vessels. The proposed method is just allowed to measure the heading angle, and by this measurement, we are estimating heading rate and total disturbance caused by environmental forces, wind, wave, and low-frequency waves, and also loss of effectiveness and the actuator force that comes from loss of effectiveness and bias. The tracking error for the heading angle and actually for the filtered virtual control, both of them are guaranteed to be confined in funnel boundaries, which is also critical, and guarantee both transient and steady-state performances for us. And simulation results demonstrate the applicability of the proposed method. For future work, we can considered dynamics of the rudder. Here, we didn't consider the dynamics of the rudder. It's very important. We have saturation, we have rate limiter. It should be considered. The robust stability and robust performance of the closed-loop system in the presence of measurement noise should be studied, because here also we didn't consider measurement noise. And last but not least, but it is very important, we have to consider also wave frequency motion. We just consider low frequency waves. It is also should be studied in the future books. And these are the references, and thank you for your attention.
Thank you, Reza. We have time for question, feedback, comments. Any question? No comments? Yes?
Thanks for your presentation. Just a curiosity, how much the heading measurement is reliable? So the gyro compass, if I understood, the heading, how much the measurement is reliable? Just a curiosity. Thanks.
It's a good question. The problem is here that we are assuming that we are using suitable sensors, that the heading measurement is completely reliable. As I mentioned, we have measurement noise, we have unreliable sensors. That should be also considered for the problem. Something that is very important is that when we have sensor faults, we may have unreliability from the sensor itself, because we have measurement noise, and we have sensor fault. This is also another problem. So in this paper, we didn't deal with this problem, and that is another point. For example, we can use unknown input observer to estimate the sensor fault, or using other methods that can deal, for example, with sensor faults in detecting and isolating sensors.
Maybe one short, do you have planned to implement your solution in real environments? Yes.
This is a problem that it's in the beginning of the way, because most of the papers and most of the works just worked on a steady state performance. Here we also focus on the transient performance. We are working to also consider wave frequency motion. It is very important because, as I mentioned here, the low frequency wave is just like a disturbance in the input. It comes and adds to the rudder fault. But high frequency waves or wave frequency motions are disturbances that comes in the output, and it should be modeled in the output. And it is like a noise and works like a noise. We can, for example, for that part, we can use Kalman filter to somehow filter it the best way, because it's active filter. We can use also low pass filter or somehow notch filter if we know the frequency wave to filter the whole, wave motion. Yep. Yep.
Thank you. Okay, thank you. We have time for one last question. No? Okay, thank you. Before going to the next presentation, I would like to know whether the fifth presenter is in the room from Aix-Marseille University. Okay, did you put your presentation on the okay, so thank you. Okay, so the next presentation is given by Anastasios from Delft University. So, Anastasios Tsolakis. Okay, the floor is yours.
Thank you very much. Good morning from my side as well. My name is Anastasios Tsolakis. I'm a fourth-year PhD student at TU Delft. And today I'm going to present to you our work with my supervisors, Laura Ferranti and Vaso Repa, on an active thruster fault diagnosis algorithm for an overactuated autonomous surface vessel. So I'll begin with the motivation of this work. Recently, we have seen autonomous surface vessels developing quite rapidly, basically in order to be able to operate independently of human interactions. And applications, recent applications include transportation, hydrographic surveying, environmental monitoring, and search and rescue missions. And there are good reasons to employ autonomy in such tasks because they promise to reduce operational costs, reduce carbon emissions, and most importantly, enhance safety. And specifically for the last part, statistics over a large period of time indicate that human action is one of the main contributors in marine casualties. And for that reason, our first work with this group was to develop a trajectory optimizer in which we incorporate the call regs, the traffic rules, and we incorporate them as collision avoidance constraints in an MPC algorithm so that the autonomous vessel can navigate in dense traffic environments while safely avoiding collision according to the rules. But then, if we look again at this graph, we see that another major reason for marine casualties is system and equipment failure. And as Abhishek showed before, we have the recent example of the Baltimore bridge collapse, where the vessel had a catastrophic power failure, which led to loss of propulsion and maneuverability, thus leading to human casualties and a logistical nightmare because it blocked the major waterway to the port. So if we think about autonomous surface vessels, we think that they will heavily rely on equipment such as sensors, actuators, and computation units. So the matter of system and equipment failure is even more urgent. So that made us think, how can we enhance safety in our motion planning algorithm in presence of faults? And that set the goal for this work, which is to design a fault detection and isolation algorithm that for actuator fault diagnosis of an overactuated ASV working in tandem with our motion planner. We use also the Tito-Neri scaled vessel model, which we assume that it performs a planar motion. So it has X, Y, the position, psi, the heading of the vessel, and UVR are the respective velocities. And then this vessel is actuated with three thrusters, two azimuth thrusters at the back, where we control the magnitude of the thrust and the direction, and one bow thruster in the front, which we control only the magnitude. And we model this with Fossen's equation of motion, where the first autonomous term models the inertia, hydrodynamic effects, etc. We have an input map that maps the input of the vessel, this vector here, to the dynamics, and also a disturbance term that maps the wind, disturbance forces, etc. to the system. We also assume that we have access to measurements that measure the full state, which is corrupted by an unknown noise signal. And the faults, in this case, we consider actuator faults, which are known as loss of effectiveness, which are these parameters, eta parameters, multiplied with a thrust. And in healthy condition, we have a value of 1. In faulty conditions, we have a value less than 1. The faults are single, and we assume they happen abruptly. In order for our method to work, we make two major assumptions, that the disturbance and the noise signals are unknown but bounded, and that the bounds are known as well. So as an overview, what we do with this algorithm, we rely on input and output measurements, which we use to design residuals and adaptive thresholds coupled with these residuals. And then we, based on these redundancy relationships, we basically use them for fault detection and fault isolation. And for fault isolation specifically, we use actuator redundancy of our vessel and reconfigurable MPC. So we reconfigure the MPC controller we had before to be able to isolate the faults. And that leads to an algorithm that has FDI, motion planning, and control allocation in one without the need for a control allocation module and by also satisfying actuator limitations. So for the residuals, we start with the system dynamics of our system, and we design a nonlinear Lumberger observer with a correction term. And we define the residual as the difference between the measurement of our actual system and the measurement given by our observer. Then we substitute the measurement equations in this equation, and by using the triangle inequality, we can derive an upper bound for this quality, basically for the norm of the residual, which is to be interpreted element-wise. However, the right-hand side of this inequality is unknown because it depends on the state error, which is unknown. So the next step is to find a suitable adaptive threshold to bound this residual. And to do that, we combine the previously shown equations to derive the state error dynamics, and then by basically multiplying with an exponential term and integrating this differential equation, and using the triangle inequality again, we derive an upper bound for this state error bound, which depends on an initial term that will soon die out because of the exponential, and a beta term, let's say, that is constantly, let's say, giving some bound. Now, of course, this term here, the state is unknown, as we said before, so we need to find an upper bound for this as well. For that, we use interval arithmetic and the triangle inequality to derive an upper bound for this. And since the noise and disturbance have known bounds, then we can, we know this quantity xc inside, and then we can numerically integrate this equation online in order to derive this term beta here. And thus deriving an upper bound for this state error bound. So combining the expression for the residual and the threshold, we can derive these analytical redundancy relations, which basically say that in healthy conditions, this should be satisfied element-wise. But if, in any case, any of these conditions is violated, then we have a detection. We have detected that the fault has occurred for this discrepancy to happen. And also, we combine this with we design a Boolean variable, a simple Boolean variable, to indicate if such fault has occurred. Now, for isolation, we take the Jacobian of the input map with respect to the fault parameters, so as to show which ARR is sensitive to its respective fault in the columns. And the first part of the matrix is a zero matrix because these states are not directly affected by these faults. But the lower part of the matrix, you can see that it gives us a fault signature matrix that is of rank 2 because the first two columns are identical. So it's rank deficient, which is not possible to isolate between those two faults. So what we need is to differentiate these two columns by placing a 0 in any of those. And for that, we can get a fault signature matrix of rank 3. Then we shift our focus to these two terms, which correspond to these columns of the fault signature matrix. And we need to set them to 0 for any value of the input. And this is possible because these are nonlinear algebraic equations that can be solved analytically. And solving them gives us a value of the azimuth angle, alpha r, which constantly sets this, for example, this term to 0, therefore allowing for isolability. So how we do that online, we use the reconfiguration of our MPC controller via the cost function. So we introduce a soft constraint where we activate that when we see that a fault has been detected but cannot be isolated. And then we continuously compute the residuals, the thresholds, and thus the decision vector here, which we compare with the fault signature matrix that I showed you before. So as an overview, we get in real time input-output measurements. We compute the residuals and the thresholds. And then if we detect a fault, then we start the isolation process, where we check if the fault is in the both raster, in this example, or else we continue with reconfiguration so as to be able to distinguish between one of those two faults. So we tested this in simulation scenarios. We have a simple traffic scenario here, a starboard crossing scenario where the autonomous vessel needs to perform a collision avoidance maneuver behind the non-autonomous vessel. And we inject the fault at time equals 6 seconds, which is an 80% loss of effectiveness of the right thruster. So that's unfortunate. The video doesn't work. But so yeah, sorry for this. The video would show that as the vessel performs the collision avoidance maneuver, we have in the beginning so in the red line you see where the fault is injected. Shortly after, the fault is detected, and then the reconfiguration starts because it has not been isolated yet. And shortly after, we see that the second detection variable is also is activated. Basically, the ARR is, let's say, not satisfied. So we get a decision vector that indicates that the fault is indeed in the right thruster. Regarding the state of the system, you can see how the vessel, after the fault, cannot follow the reference velocity. You can see how the thrust, the real thrust that acts to the system is much less than what the controller thinks. And here you can see when we constrained our azimuth in order to perform the isolation. So in this work, we presented an active actuator fault diagnosis algorithm for an overactuated autonomous surface vessel. For detection, you used nonlinear observers for the residuals, coupled with adaptive thresholds to reduce conservatism. For the isolation, we exploited the redundancy of our system, along with a reconfigurable model predictive controller for active diagnosis. And the method has no false alarms by design, but it is prone to miss detections, and these depend on the severity of the faults on the system. For future work, now we are currently working on a fault estimation algorithm to estimate the fault parameters and some bounds for them, so that we can later close the loop and use them in a reconfigurable fault-tolerant model predictive controller. And we also plan to migrate this code to ROS2 so that we can perform experiments with the real vessel that I showed you before from the lab. So thank you very much. This concludes my presentation.
Thank you so much. If any question? Is there any question? Yeah.
Thanks for the presentation. I have one question. Was the collision avoided after the reconfiguration? So Was the collision avoided after the reconfiguration? So was the system effective enough?
Yes, thank you for your question. Indeed, even after the default, the avoidance was still, collision avoidance was still possible, and this is because MPC has some inherent robustness in a model mismatch, because a fault is basically a model mismatch. But it is not guaranteed that this will work in the sense that if, for example, this works in a more congested traffic environment, the mismatch could be as much to basically have a, a displacement of the vessel that is causing a collision. So it's not guaranteed that it will collide, but it's not also guaranteed that it will not collide. Thank you very much. Yes.
I just want to ask you about f of y minus n. You mentioned that you approximated it. Yeah, can you more explain? Yeah. Yeah, this one. Yeah, yeah. You missed it. Yeah.
This one.
No. Can you the next slide? No, f of y minus n. You mentioned that you, in the adaptive threshold. Yeah. Yeah, this one. Yeah.
Yes. So for this. Yeah. So for this, the state is unknown, but we know that the state is basically given from the measurement equation, depending on the measurement, which makes it adaptive, and the noise, which we assume is bounded. So because we don't know the state, we can find an interval for the state based on this quantity here. Worst case scenario, we basically add the bound of the measurement noise to the measurement. And then we use interval arithmetic, which is basically a generalization of the simple computation process like addition, multiplication, that extends this to intervals. So we basically get an interval for f as well. And then by using the triangle inequality, we can bound with this interval that we found. Of course, this introduces some conservatism, which means that misdetections can occur if the bounds are taken too large. So far, we haven't made an assumption of that, but this can indeed be used in order to derive the bounds based on Lipschitz continuity. Yes. Thank you very much.
Any other questions? Okay. Thank you. Okay.
Thank you. So the next presentation is given by Nikos Kougiassos from Delft University as well. Sorry. I don't. Oh.
Thank you. Can you also make it full screen? Okay, so good morning everyone also from me. My name is Nikos Kougiassos and I'm a fourth year PhD candidate at TU Delft, also supervised by Vaso Repa. So my colleagues before, they talked about these really nice diagnosis schemes, and in some way or another they thought that we have some sensors and we probably decompose these sensors into sensor sets. So this is exactly the topic of my presentation. We will take one step back and see this sensor set decomposition in order to enhance the fault isolability for marine propulsion systems. So starting, maritime safety is really important. For modern vessels, we cannot imagine boarding a vessel that's not safe, but it's also a basic pillar for the development of future autonomous ships. At the heart of the show, we have the propulsion system itself, which you can see in this figure for an example of hybrid propulsion. And This is actually the heart of the vessel. This is, you can imagine, a large-scale application like a factory inside the ship itself, incorporating many different systems with heterogeneous dynamics, many interconnections between them. Despite its importance, we unfortunately see that we have a lot of accidents in marine vessels due to system or equipment failures, and these amount up to 26% of all the accidents, according to recent statistics in 2023. Whereas we also have a considerable amount of vessel casualties due to loss of propulsion. And you might think that 7% is a small number, but you can see that in the recent case of the Baltimore bridge accident, the consequences of such a casualty can be very severe. So that's how we deem that the propulsion system is indeed safety critical. In order to improve the safety, because this is our target here, we need novel and efficient diagnostic systems. And actually, we examined what is there currently, and it seems that we only rely on hardware redundancy, both in literature and in practice. So we have, for example, multiple hardware sensors of the same type. Whereas we could also use models that we have developed in order to construct analytical redundancy instead, for example, in the form of virtual sensors. And what I mean by analytical redundancy in this case is the combination of the models that we have plus the hardware sensor measurements to reconstruct the lost information. So we can transition from using single sensor values to actually a collaborative framework between the different sensors. The questions we are asking here is how can we optimize the design of the diagnosis approach? And in literature, there are mainly two tasks associated with this problem, the sensor placement problem and the sensor set decomposition problem. And in this presentation, we'll focus on the second one. Regarding the sensor placement, usually we have objective functions related to the cost of sensors or the number of sensors that we are using, whereas some authors also include other requirements like fault distinguishability requirements. For the sensor set decomposition instead, we focus on observer stability and isolability of sensor faults. Looking in the marine literature on how this sensor set decomposition is happening, we find two approaches. First, we have the physical papers using the physical decomposition of the systems themselves and just expanding it to the decomposition of the sensors. And this is something very easy to perform, but it's not necessarily optimal for diagnosis. What we could do instead is use some simplified models, thus mitigating the complexity that we are assuming, but in this case, we can only model a limited amount of sensors. So, in the presentations of Abhishek, in the presentation of Tassos, you saw this fault signature matrix, and these are directly related to isolability. And so the main research question for this presentation is how can we decompose the sensor set in sensor subsets, automatically generate the fault signature matrix, and because we're considering a distributed architecture, we have local matrices Fi and global matrices Fi, and we want to enhance the architecture based on sensor fault isolability. Here in this figure, you can see an example. So if we view the sensor set with 3 sensors as a lattice representation, then we can choose, for example, one sensor subset being just the first sensor, and the second subset being the other 2 sensors. The basic assumption we are making is that we consider that the modules, the monitoring modules that exist inside the monitoring agents, only use one analytical redundancy relation each. Going on to the modeling, I told you that here we're considering really complex systems. And for those of you who also followed my presentation in the previous SAFEPROCESS 2 years ago, you have seen the high nonlinearity of the system itself and also the multiple interconnections. Instead, to mitigate this complexity, we are using a qualitative modeling technique that's based on semantics. So here in this figure, you can see a typical control system representation, but instead of just a monolithic system, I want you to imagine that we have sets of actuators, set of sensors, sets of systems, and so on. Then we can construct a components database that's comprised of two parts. First is the system part, FP. This is a database concerning to the systems, and all the rest are related more to the automation aspect. What I mean by semantic information, we can, instead of using models, we can describe our system using language. So we can say that the system requires this input and provides this output. And also we can incorporate other characteristics, for example, the units of measurements. If we have this input and output information, in previous work we have also suggested an automated algorithm that is able to do this input-output matching in order to create the knowledge graph of the system. So we have a graph representation of our system. So in order to perform this sensor set decomposition, this is the main methodology that we are proposing. And it's all based on a greedy stochastic optimizer approach. But let's take things in order. First, we need to set up the sensor set decomposition problem. So the objective function, we are trying, as I said, to optimize isolability. So we are trying to maximize the number of unique columns in the fault signature matrices. Here, because we have a distributed scheme and we have multiple local matrices, we find that it would be conservative to just consider the sum of the ranks of the local matrices. And here you can see an example. Let's say we have two agents. If we consider the rank of the first one, it's just 1 because we have only one unique column, and the rank of the second is 3 because we have 3 unique columns. So we propose this transformation phi that actually takes these two matrices and combines them in a single matrix that has rank 3. The second part is the rank of the global matrix, F chi. And the decision variables are the number of sensor sets and also the composition of these sensor sets. Looking at the constraints, first of all, we want to decompose in such a way so that the sensor sets are not overlapping with each other. The third constraint, equation number 3, says that we might not use all the available sensors to us if they are not beneficial for diagnosis purposes. Then we somehow need to limit the search for the decomposition. We cannot have an infinite amount of sensor sets, so we impose a limit on this. And the final one is because we're considering virtual sensors, and as I mentioned, virtual sensors require hardware sensor measurements. We need this sensor set requirement to be part of the decomposition. The next step is to construct the architecture, and to construct the architecture, here we use semantics. So I told you how we can create the knowledge graph, and based on the knowledge graph and the decomposition of the sensors, we can figure out the architecture of the monitoring agents in the local level, and then just implement also the global agent. From then on, it's trivial to generate the fault signature matrices because we know the agents and we know the interconnections. So the greedy stochastic optimizer starts from a random valid sensor set decomposition and iterates in this scheme until we get the highest cost value. Now for the simulation setup, we assume that we have the hybrid propulsion system that I previously showed you. And here we have 12 hardware and 13 virtual sensors, with the hardware sensors and their IDs in the semantic database being recorded in this table here. Now a question for the audience. Looking at the system itself, how many monitoring agents would you create for this system? Who says above 7? Can you raise your hand? Above 7. Less than 7? All the rest, I presume. The less than 7 is a right choice, I believe, because the more we increase the number of monitoring agents, then the more communication requirements we're going to have. So nothing is for free. We pay through communication. And here I'm a bit more conservative also. 7 is a rather large number. So we go from 1 up to 5 agents. And for each case, we do 30 runs of the algorithm, so 30 random decompositions. We start with 20 random decompositions. And at the end of each run, we have the optimal decomposition. I'm personally a fan of simple results, so here you can see a simple graph of the results. So in the y-axis, you can see the maximum achieved value for the cost function for each number of agents. And the horizontal axis is the number of the considered agents. So as you can see here, for the cases of 1 or 2 monitoring agents, we see no significant improvement in sensor fault isolability because we result in 2 agents that are very interconnected with each other. Then we notice that a big jump happens from 2 to 3 agents, rendering more isolable columns. And then we have, in smaller increments, from 3 to 4 and 4 to 5 agents, more unique columns. Of course, we cannot continue this indefinitely because of communication, but I think it's a solid start. And here you can see an example of the produced matrices for the 5-agent configuration. I show you an example from the matrix of monitoring agent 1, and also the global agent FKI. Okay, maybe this is too much information in one slide, but in the discussion step, in the table of monitoring agent 1, we show that we have 9 out of 11 unique columns. And also in FKI, we show 5 out of 11 unique columns. If you're concerned about the interconnections between the agents, 4 out of 11 faults affect all 5 monitoring agents, 6 out of 11 affect at least 3 agents, and 11 out of 11 affect at least 2 monitoring agents. Another interesting result, I mentioned that we assume that we don't have overlap between the sensor sets in our decomposition, but it turns out that if we extrapolate the decomposition also to the systems, we found out that overlapping system decompositions might be beneficial for diagnosis indeed. So we designed this SFDI designer module that managed to decompose the sensor set, automatically generated the matrices, and also enhanced the architecture based on fault isolability. Regarding the application, the main contributions are the enhanced isolability of sensor faults for marine propulsion systems, and the fact that we use also virtual sensors aside from the hardware redundancy. Whereas the theoretical contributions include the handling of the sensor set decomposition problem for a distributed monitoring architecture, and also that we used semantics to perform this decomposition. And this is how we linked qualitative models, and these are semantics, to quantitative metrics, and these are the FSMs that we used. So I would like to thank you all for your attention. If you want, you can visit my project website and also our research group SafeNet. And yeah, I'm open for questions.
Thank you so much. If there is any question. Okay, may I ask a question? Okay, about the optimization problem, you had a maximum of cost function, and the method that you used was greedy stochastic. Okay. And can you explain it more? Because there are other methods, stochastic methods, that may give you a better result. And did you compare your greedy stochastic method with other methods, or?
First of all, thanks for the question. So indeed, we use the greedy stochastic optimizer for our approach. We made this choice because it has been applied also to similar problems in literature, although we didn't do any comparison with other methods, as you suggest. Yeah, we could also use the deterministic one, but the deterministic one, you need more runs. Yeah, yeah.
Actually, there are some evolutionary algorithms too that can solve this kind of problem, even if your problem is not differentiable and so on. But as you mentioned, it is the one that's usually used for this in the literature. Okay. Thank you so much.
Thank you.
Okay. Any question? Okay. Thank you so much.
Thank you.
Okay, we have a little technical difficulty with the next presentation. So if you agree, can you make your presentation now? If this is not a problem, okay. The time we find a solution with the next presentation. So the next presentation is given, you are Riccardo? Yes, by Riccardo from Felicetti from Politecnico delle Marche. So please. And thank you for taking the ground so far.
So thank you for the presentation. My name is Riccardo Felicetti, and today I'm going to present you one of our last works that is entitled Actuator for Tolerant Control for a Remotely Operated Vehicle based on Adaptive Extended Kalman Filter. This is just a sketch of my outline. I will introduce you the model, the fault-tolerant control scheme, the fault detection and isolation method we propose, some very brief simulation results, and finally conclusions. As you know, I'm sure, remotely operated vehicles are a class of unmanned underwater vehicles that are usually employed for tasks that are somewhat critical, such as exploration and manipulation and so on. And they operate in environments that may show many problems, such as external disturbances, marine currents, collision with obstacles, and so on. And I'm sure I don't need to convince you that there is a need for reliability, because this is the section, okay? So we need additional reliability for these vehicles, and in particular, we focus on dealing with actuator faults, okay, such as a damaged motor, a damaged propeller, or entanglement due to aquatic vegetation on our thrusters. So the objective overall is to perform fault-tolerant control for in our case, a BlueRob2 heavy ROV with 6 degrees of freedom. And I will show you how to detect actuator faults from noisy navigation data, so no data from currents, voltages, velocity, speed of the motors, and so on. And I will show how to isolate the fault and perform fault-tolerant control from this data. So just to introduce the issues, the system is overactuated, so we have to take care of isolating which motor of many is the one that has some issues. And parameters uncertainty in this kind of vehicles are somewhat inevitable. And solution based on banks of observers can be done, okay, but they become computationally heavy when you have a lot of components. So we are trying to find a smarter solution, so less heavy. And conventional Kalman filters are not so good for this class of vehicles. I will show you later why. I will be very fast with the modeling because it's a very conventional model. It's just from the literature. So I have highlighted in red the most important quantities. So eta collects the position and the orientation of the vehicle. Nu collects the linear and angular velocities. Tau is the vector of the generalized forces generated by the actuators, so linear forces and moments. And nu c is an irrotational marine current that we are including in the discussion. And nu r is the relative velocity of the vehicle with respect to the marine current. We are doing some simplifying assumptions just to simplify a bit the problem. The first one is the most important, and I will talk about it again in the conclusions. We assume that eta and the relative velocity are measured and available by means of sensors. And just to simplify a bit the problem, we suppose the body fixed frame is centered in the center of gravity. The vehicle is somewhat symmetric, so we have simpler inertia metrics and so on. And we assume also low speed movements, just to simplify a bit the modeling of the hydrodynamics. Nothing new here, the kinematics. There is very conventional rotation metrics R from the body frame to the earth frame, and a conventional transformation matrix T that maps the angular velocities. And thanks to the assumptions I've made before to simplify a bit the model, the dynamics can be expressed by very conventional, it can be found in the literature. This is the nonlinear model of the vehicle. Let's go to the point. We assume that the vector tau, that is the generalized forces generated by the thrusters, can be modeled as B times W times F, where B describes the configuration of the actuators. W is a diagonal matrix we introduced to model multiplicative folds on the actuators. And F is our vector of forces generated by the single actuators. And we assume F is the control input. We neglect for now the part regarding the speed of the motor and so on. F is our control input. So just an overview of the fault-tolerant control scheme. Quite conventional, I have to say. So we have a control law that produces a vector tau c, that is the virtual control input that we want to achieve, and a control allocation algorithm that calculates F, so the forces in each motor, to achieve that tau c. But in our case, our control allocation is a fault-tolerant control allocation. So it takes into account an estimation coming from an FDI algorithm of the faults acting on the motors. We consider a very simple trust allocation algorithm, but without loss of generality, we can do the same thing for any other trust allocation algorithm, constraint or not. So we just use a pseudo-inverse to calculate F. And we have two cases. When the FDI algorithm evaluates that one thruster is healthy, then we can just set Wi hat equal to 1. Otherwise, if the FDI algorithm evaluates the thruster to be severely damaged, we put Wi0 equal Wi hat equals 0. In this way, we just switch off the actuator because the system is redundant. Okay, let's go to the residual generation part. So the first step, we take the ROV model and we discretize it with a forward Euler integration, okay? And we obtain this kind of model where we have introduced noises, and theta is actually an unknown vector that collects the marine current, in this case in the earth fixed frame, but not important. And theta f, that is the effect of actuator faults on the thrust generated by the actuators. The rest is just coming from the forward Euler integration. What happens? you can see that you can consider x and theta to be an extended state to be observed. And if you can see that the simplest model that can be employed to model something that we don't know the dynamics is just assume it is constant. But, well, here we have no sensor noise, no noise. We don't know how to model this noise, okay? So what happens is that the augmented state is not uniformly completely controllable from the sensor noise, because very simply, there is no noise here besides theta, okay? So it's not easy to employ a conventional Kalman filter, adapt an extended Kalman filter, because we don't have the value here. If we just put the noise to be 0 in this equation, then the Kalman filter thinks this is deterministic, non-stochastic. So it does not update the estimate anymore after a certain time. So it's not effective for fault detection. What we employ in this case is a recent adaptive Kalman filter that has been proposed by Zhang in the linear version and then straightforwardly extended by Scriver to an adaptive extended Kalman filter formulation. As for the fault detection, we just employ the estimation of the fault effect coming from the adaptive extended Kalman filter, and we compare it, we weight it and compare it with a fixed threshold in this case, and if the threshold is overcome, then we detect a fault. If we detect a fault, we move to the fault isolation phase. In the fault isolation phase, we want to find which actuator is damaged, if any. Just a bit of math. If there is if the fault status is equal to our estimation, then the commanded and the actual generalized forces coincide. Otherwise, just taking the difference, we can see that we can express the difference between the real and the commanded generalized forces in this way. We can rewrite the last expression in this way, if you want, where you can see that theta f is expected to be the weighted sum of fi times bi, where fi and bi are the columns of f and b. So fi is a scalar indeed, and b is the column I of matrix B. So if you assume just our estimation theta fk hat is expected to be directional, and the direction is just a subspace with dimension 1, and the basis is bi, the column I of B. We can perform isolation because each pair of columns of B is linearly independent, pairwise. So to isolate the fault, we just want to check the direction of theta hat, so the estimation of the fault. And the most straightforward way is to check the cosine similarity against the threshold. We just check the similarity between our residual and the column I of matrix B, where F is just a correction to take into account the B direction. Check for fault detection. If fault detection signals that a fault is happening, then in this case we calculate the cosine similarity, and if the cosine similarity is very high for the largest residual SIK, where I from 1 to 8 is the motor 1 to 8, then we have isolated a severe fault affecting thruster I, and the thruster is just switched off by setting WI hat equal to 0. I will show you some simple simulation results. We have injected two severe faults on thruster 1 and thruster 7, a 80% loss of effectiveness and a 60% loss of effectiveness. We have introduced motor parameter uncertainty that is plus minus 5%, exception made for mass and buoyancy because they are easier to be measured and estimated. and a plus minus 5% uncertainty in the nominal thruster effectiveness. The parameters are taken from a PhD thesis, and the control scheme employs PIDs. We didn't touch it. So it's the same. On the left, you can see what happens when a fault occurs. The vertical dashed line represents the instant where a fault is injected. And you can see the departure from the reference is not so much. It can be considered acceptable. The output of the adaptive standard Kalman filter also includes an estimation of the marine current. You can see that even during the transients, so when the marine current is not constant, the estimation is quite good nonetheless. On the top right figure, you can see the fault detection procedure. So just focus on the solid black line that is the weighted residual, scalar weighted residual, and a fixed threshold 2. When a fault happens, the residual goes up very fast, overcomes the threshold, so we check for cosine similarity. Here we have calculated the cosine similarity everywhere at every time instant, but it is not necessary. We could just calculate it when the fault is detected, so here and here. So in this case, S1 overcomes the threshold, so actuator 1 is the faulty one. And in this case, the dark red residual overcomes the threshold, so again, motor 7 is isolated to be faulty. And here you can see the effects with the fault-tolerant control. On the left, you can see just the fault effectiveness and its estimation, and just to evaluate the delay in detecting the fault. And here you can see how the thrust is redistributed when we update the matrix W hat. That includes the estimation of the effective actuators. So just to conclude, we have proposed a fault-tolerant control strategy that is applied to achieve fault-tolerant control for a Blue Rob 2 heavy ROV as a case study. Some remarks. We have assumed position, orientation, and relative velocity to be available. This is a very important assumption. Otherwise, we have to reconfigure the scheme. And the Kalman filter returns an estimation of the state, the faults, and the marine current. If only the absolute velocity can be measured, so we are in a different set, we have two alternatives. If the marine current is unknown, well, it works only in absence of marine current. Otherwise, if we know the marine current, we can redesign the Kalman filter on the dynamics equation only, so we neglect current estimation. And in our future works, we are going to introduce active fault diagnosis to improve this aspect, so to work even when we have an unknown marine current. And we are also dealing with a practical case of multi-rate measurements. It shouldn't be difficult to include it in our formulation. Thank you.
Thank you so much. If there is any question. Yeah.
Yes, thanks for the interesting talk. I just have the same question as to Professor Ron Patton. I saw you inject faults with the LE with 70 and 16, right? So if it's like mean of the fault, like maybe only 10% or 5% or 20%, actually for the baseline control, they have some adaptive abilities to accommodate the fault. So for your case, 60% or 70%. So you have full confidence in the full FTC. But in what cases the FTC will lose control? I mean, for what type of fault? Thank you.
Okay, yes, indeed, we employed large faults because we assume for very small faults, the low-level control just can't tackle with it. So if an actuator is 5% less effective, it shouldn't be an issue for the baseline controller. As I told you before, the actuator effectiveness is indeed uncertain. We assume the plus minus 5% uncertainty on the actuator effectiveness, and that is perfectly fine for the baseline controller. But if we have a severe fault instead, the baseline controller does not perform well and the vehicle drifts from its trajectory. So yes, the larger the fault and the easier to be detected by our scheme, of course. Anyway, if we have just a single fault as severe as you want, even 100% on one actuator, the control scheme still works because it is redundant. So we have actuator redundancy. The vehicle we consider as 8 thrusters, okay? So if just one is completely failed, no problem. If 2 are failed, well, depends which couple of actuators are actually failed, okay? So yes, if 2 actuators on the same side are completely broken, it's quite hard to control the vehicle. Otherwise, as you can see here, we have just switched off the thrusters, okay? We didn't even try to estimate the real thrust effectiveness of the actuators because of the model uncertainties and so on. It's quite hard to estimate it, and also because the vehicle is redundant. So we just switched it off, and with 2 motors switched off, so even fully broken if you want, the tracking is still fine. Well, not if you broke the motors exactly on the same side of the vehicle. I hope I have answered to your question. Exactly, because this is just because we have a severe fault. We are losing so much power that it's somewhat useless to try to identify 17% efficiency remaining or 18%. We just switch it off to avoid any problems in the estimation, and that's a very simple solution, I admit.
Thank you for a very nice presentation. I'm curious as to how you estimate the thrust from your thrusters. The reason I'm asking is that we use the blue ROV model as well, and experience that the thrusters are extremely sensitive to local velocity from water flow. So we had to measure current to the motors as well as RPM. How do you do it? How do you estimate the thrusts from the individual thrusters?
Thank you for the question. Yes, the gold standard is to measure currents, thrusts on motor velocities, for sure. Okay, in this case, the estimation is valid because we assume quite a limited speed. As I introduced before, we assume low vehicle speed, okay? So the effects of high speeds on this thrust is somewhat limited. Anyway, we focused on F, on the produced forces. If you go down to the actuator speed, it becomes much more complicated, I know. And I think this works in limited velocities. If you overcome a threshold of acceptable operating conditions with significant relative velocities with respect to the marine current, yeah, I think it's much, much harder to do this. So estimating it from navigation data only by means of model-based design. Did I answer to your question? Okay. Okay, thank you.
Thank you so much. Okay.
Thank you. So we move to the last presentation given by it's Aya Youssef, right? From Aix-Marseille University. Okay, please, the floor is yours.
Okay, so hello everyone. Thank you for your attendance. I am Aya Youssef, a PhD student at Aix-Marseille University. I am working under the supervision of Hassan Noura, Mustafa Al-Adil, and Mustafa Oletsin for the TNTM project for CMA-CGM. We will go through an introduction, then we will talk about the diesel engine and go through the different fault diagnostic techniques used, and then we will talk about the recent data-driven techniques used for marine diesel engines, and we will go to a conclusion and perspectives. Introduction. In 2022, and due to the COVID-19, 0.4% contraction of maritime trade occurred, which was projected to increase in 2023 by 2.4%. And due to the Ukraine war and after the Russian Federation's, the EU searched for new export crude oil and refined products, which led to long-time highs in oil cargo distances. And the marine diesel engine market surpassed a valuation of $4.7 billion, which is experienced to increase by a compound annual growth rate of 4.8% from 2023 to 2032. The marine diesel engine is crucial for powering the propulsion and the energy systems of the vessel navigating for high seas. According to the statistics, the most system to be vulnerable to damage in the vessel is the engine, sorry. So any fault on a critical component may cause a collision of the vessel, which makes development of fault diagnostic techniques very important to ensure safety and enhance predictive maintenance and save costs. Diagnostic techniques went through 3 generations. The first generation from 1960s to 1990, where traditional field testing techniques was used, which requires expert engineers and technicians. And then the second generation from 1990 to 2010, where they used online condition monitoring and remote fault diagnosis using alarm systems. And now they are using intelligent fault diagnosis by implementing many sensors and collecting data. The diesel engine is an internal combustion engine, which is mainly composed of 5 subsystems: the fuel injection system, air intake system, exhaust system, and lubricating and cooling system. The fuel injection controls the amount of fuel for combustion in the cylinders. And to ignite the fuel after compression, the air intake system applies filtered air to the cylinders, and the exhaust system collects and eliminates the combustion byproducts and manages emissions to comply with environmental standards. While the lubricating system reduces friction and cleans the parts and dampens noise and vibration. For the cooling system, it maintains the temperature of the parts of the engine, and it's done by either by water or oil cooling. Okay, we have 2 types of fault that may occur on the engine. Control system faults, which may affect the software and the hardware systems, and the actuator faults, which may affect mechanical or hydraulical systems. Due to the interdependence between parts, any fault may have a cascading effect on another part. We have 3 types of diagnostic techniques that are used. The model-based techniques, which relies on building a mathematical or physical model, and diagnosis is done by residual analysis, parity space, or observer-based or parameter estimation. Few developed a physical model for this purpose. Empirical knowledge-based system techniques, which are known also as expert systems, which relies on specialized expertise of engineers and use rule-based fuzzy logic and case-based neural network. Tasdemir developed a fuzzy logic system, and the most used technique is the fuzzy logic and expert systems. For our topic, which is data-driven techniques, which rely on availability of abundant data, we have AI techniques and machine learning, which may be supervised or unsupervised learnings. The process of data-driven diagnostic techniques starts with pre-processing of the data, which takes about 50 to 80% of the process. And then the data is split to training set to build the algorithm, and testing set to validate this algorithm in order to detect and isolate and achieve diagnosis. Data-driven fault diagnostic techniques. Faults on the injection system may occur on the injectors, injector pumps, and fuel pumps, which may cause loss of combustion efficiency, increased engine emissions, and elevated noise levels. Some of the recent research papers used, like she used improved refined composite multiscale dispersion entropy, where he used repression and vibration signals in order to diagnose injection faults by selecting the features by using IRC MDE and splitting the data, and then reselecting the feature using a fast correlation-based filter, and then splitting the data and applying separate vector machine for diagnosis, which showed 92.12% accuracy for diagnosis. While Shen and Liu used the genetic algorithm Elman neural network and support vector machine using sensor data like speed, power, maximum burst pressure, and others, this method showed 95.67% accuracy for diagnosis of injection system also. While Hu used the PCA with SVM, he applied different methods to ensure that the SVM with optimized sample space optimization is the best for this to achieve the highest correct diagnosis ratio, which is 93.9%, and the lowest fault misclassified ratio, 6.1% between RBF and MLP, OSVM, and others. For the intake and exhaust system, the intake system may experience different faults like insufficient air supply and turbocharger failure, which may cause poor combustion, increased engine emissions, and decrease in engine performance. While the exhaust system may experience exhaust valve leakage early or late or opening or closing of the exhaust valve, which may cause increase in exhaust temperature, increased engine emissions, and also power loss. Some of the recent research done, you used generalized learning on two different engines, the CDK20 and the ZC6170, where he used built 5 different methods by using acoustic emissions like PCA SVM, 1D convolutional neural networks, and deep adaptation network, and 2 other methods. By implementing this method, the DAN and DAN and MDD showed the better generalized diagnostic methods. While Kai used the modified VGG16 deep convolutional neural network for valve leakage detection, this method showed 95.2% accuracy in diagnosis. And Wang also diagnosed exhaust valve leakage, where he used the semi-supervised learning by clustering the data by using k-means optimized by PCA, and then he applied on the clustered data supervised learning by using backpropagation neural networks for diagnosis. For Wang, he used hybrid fault detection for manifold learning for anomaly detection for exhaust valve. Tu and Tseng used kernel PCA, which is a nonlinear version of principal component analysis, and for feature extraction and pre-processing. Then he applied the support vector machine. This diagnosis method showed decreased the computational cost of the model. And Zhong used semi-supervised PCA by applying then the Hotelling coefficient in order to detect the anomalies. While Basurko and Yoriondo used artificial neural network by pre-processing and splitting the data into three steps: training set, cross-validation set, and testing set for diagnosis of the air intake system. And finally, for the lubricating and cooling system, the lubricating system may experience oil deterioration, drop in lubricating oil pressure, which may cause wear for the parts, and increase of engine temperature and elevated noise levels. While cooling system failure may cause increase in engine also part temperature, loss of lubricating properties, and premature ignition. For recent research, Wang used multivariate statistics by using PCA and Hotelling coefficients for anomaly detection, and then he used Bayesian network for fault isolation. For Sahin, he used 13 different supervised learning ensembled with bagging ensemble or with blending ensemble. The bagging ensemble combines homogeneous learners in order to reduce the variance of the method, and the blending ensemble combined heterogeneous learners in order to decrease the biased error. With bagging ensemble, the gradient boosting classifier showed the better diagnosis accuracy with 98.08%, while for blending ensemble, the gradient boosting classifier with random forest showed the highest diagnosis accuracy with 98.43% and construction time of 86 seconds. And finally, Liang used the autoencoders and residual analysis. He built the encoder with 2 encoders and 1 decoder to reconstruct the data, and then applied on the residuals the sum of squares of normalized residual and the sequential probability ratio test. The SSNR showed early detection, which enhanced prognosis, and the SPRT showed accurate time detection. As a conclusion, we have many limitations in data-driven techniques on marine diesel engine due to the complexity of the engine, and it's not easy to collect all data necessary for our task. And the quality of data usually is not that good due to the high vibrations in the engine. For that, we will add, the future work is to address limitations for enhanced robustness and enhance applicability for entire subsystems, explore fault isolation methods, and investigate other diagnostic techniques. Thank you for your attention.
Thank you. Is there any question?
Yes. On your problem, why did you choose to start by studying data-driven techniques? Do you have a specific set of data on your systems, or if you can develop the data and the kind of data you have?
In my PhD, I'm working on data-driven techniques in order to perform online diagnosis. We are now currently working on the liner diagnosis faults for the liner, of the cylinder. So your question is what kind of sensor data we have? Yes, exhaust temperature and cylinder pressure and the liner temperatures. Now we are working on. I don't know if I get.
Thanks for the interesting presentation. I want to ask, considering an engine as a control system, okay? So, for example, I saw you need a lot of subsystem for the diesel engine, but if we consider this engine as a control system, so what's the control input and what's the state and what's the output? For example, if we need to design some mode-based for detection or diagnosis, I knew your focus is on data-based, but I want to know, can you give us some general ideas? What's the control input here and what's the output? How to build a model for this type of engine? Yeah, thank you.
The question is, roughly speaking, how would you model your engine if you were to use model-based techniques for diagnosis on this kind of system? Yes?
First of all, it's very hard to model all parts of the engine because we don't have all the equations, the related equation between the parts. We can't establish them. But to model the system, we can use neural networks and generalized methods to build the system, I think so. Not just using mathematical equations. I think we may start by modeling the combustion chamber to model other parts. I don't know if I answered you. Okay, thank you.
I want to continue. The question is here that if you have a model, if you have a mathematical model, do you prefer to use that mathematical model or you use data-driven?
It is easier to use a mathematical model, but it is not realistic because there is no mathematical model that generalizes all the system. So I prefer use data-driven techniques in order to, for future work and to achieve more diagnosis of the system.
Okay, any other question? Okay.
Thank you. So I think we can close the session and thank again all the speakers, the organizers, and the attendants. Thank you.
I'm still looking for the speaker of the third paper on the problem of onboard risk assessment for levee hunting. Mr. Kyriakos, are you here or not? Not yet, okay. I think we should start the session. So the session is titled FDI for vehicles and traction. Sorry. Okay. Thank you very much. So the title of the session is FDI for vehicles and traction system. We are gonna have 5 excellent presentations. The first one is set-based estimation of battery and of discharge for the electric vehicles, presented by Xuang Zhang from the University of Catalonia. The floor is yours.
Good afternoon, everyone. Thank you for coming to my presentation. I'm Shuang from Yili Institute of Robotica and Information. Here the logo, what is it? Oh, I hope it won't influence. Where it come from?
For some reason.
If you go to the home screen.
Oh, it's
no?
Try again.
Okay, no, it's fine. Yeah, so I'm from ILI and the UPC. This work is under the supervision of Professor Vicens Puig and Salah Ifgir. The topic is set-based estimation of battery end of discharge for electric vehicles. My presentation will divide it by these 6 sections. If you have any question, I'll be happy to answer at the end of my talk. So now let's get started. As we know, electric vehicles has been widely used nowadays, and in the city you can find a lot of electric vehicles, and because it's more environmental friendly, which is attributed to the usage of battery, such as lithium-ion batteries, solid-state batteries, etc. So, as a battery is the only one power source for the vehicles to operate. It's essentially for the users to know how long time left for the battery to maintain the operation. So it comes to the main problem of this research, that is how to forecast end of discharge and the remaining useful life for the batteries. And it's also one of the main tasks for the prognosis. Before moving to prognosis, I will illustrate some concepts. End of discharge and remaining useful life in the battery prognosis domain is related to state of charge. SOC is the proportion of the total charge available. As the name implies, end of discharge can be determined when the state of charge reaches to threshold, and it means it lies outside a given region of acceptable behavior. And the remaining useful life in this research, it is remained to the remaining discharge time. Then let's review some literature regarding the end of discharge and the remaining useful life prognosis. In this research, we mainly focus on the model-based prognosis. It basically consists of 3 basic problems. A state estimation problem, which aims to obtain the unmeasured state by means of a state observer. Then a state prediction problem aims to propagate the system model to predict the future state. Then finally, a computation problem for the end of discharge and the remaining useful life, as I said before, is concerning when SOC reaches the threshold. Then one main problem existed in the process of prognosis is the uncertainties. It's inevitable, and it may come from like measurement noises, model uncertainty, and future uncertainties. And in the literature, there are two families of approaches to describe the uncertainties: stochastic approach and deterministic approaches. In the stochastic approach, they are based on probability density function of the uncertainties. For example, common filter, it deals with Gaussian noises, but it's not realistic because not all uncertainties have follow Gaussian distribution. Then another choice can be particle filter. It can deal with non-Gaussian noises, but the cost is it has intensive computation. So it's normally time consuming. Well, time is very important in prognosis. Imagine if the prediction computation time costs similarly as the real running time, then the prognosis is innocence. It's nonsense, sorry. Then it comes to set-based deterministic approach. It is both efficient and no distribution assumption. It simply assumes the uncertainties are unknown but bounded. Because, due to it provides a bounded range for the uncertainties, then it can provide a more reliable prediction result. Then here are some typical type of sites to describe these uncertainties: intervals, ellipsoids, and the zonotopes. If you come from the Compostelle talk, you can maybe have some idea about the zonotopes, and which is also the main technique we use in this research. The intervals has a simple computation feature, but it's not compact as compared with ellipsoidal and the zonotope. Ellipsoidal site is more compact, but the computation is more complexity. Well, zonotope is like a good compromise between these two options. It's more compact and it has efficient computation, and it also closing under Minkowski sum. So in this research, we use zonotope to describe our uncertainty. And here is the uncertainty, here the definition of the zonotope. As you see, it's composed by two parts. Under the angle bracket, C means center, and R is a shape matrix, which represents the generator segment. In fact, zonotopes has been studied a lot in the domain of fault diagnosis, but in the domain of prognosis, it's quite limited. And also, there's no direct application to forecast the end of discharge and remaining useful life for the battery system, which is also the main motivation of
the ample force or the deflection. However, our paper is restricted to the fault estimation framework, where you try to estimate the fault in this damper. And the novelty of this work is considering varying chassis mass, so we consider that the mass of the vehicle is changing. Now let's look at the modeling of this system. This is a simple quad-car model of a corner of a vehicle. MS is the sprung mass, so the mass where the passenger sits on. And US is the unsprung mass, which is the mass of the wheel. The wheel is modeled as a spring of stiffness KT, and the elements that connect these two are the suspension. In here, we obtain the dynamics of this system following Newton's second law of motion. So Fs and Ft are the spring force and the tire force, which can be expressed as a linear function of the state. And FD is the damper dynamics. So the damper has two parts, FD, which consists of the linear parts, and then there's an electrorheological part, which is non-linear. So there's some non-linearity here, but that non-linearity is Lipschitz. And then we assume that there is some forms of unknown dynamics that we call the small f. So this one is added to the faulty force, and that will cause some faults in our system. And the objective of this paper is to estimate this f from the accelerations of the two masses. So you measure the acceleration of these two using accelerometers, and from this you want to estimate the fault. There are, in principle, two main fault estimation schemes. The first one is the PI1, so proportional integral observer. This one is based on the fact that you add the unknown fault into the system state as a new state. However, you don't know its dynamics, so you have to assume that it is zero. So you assume that the fault derivative is zero. You add it to the state and you estimate everything. However, this method, it only restricts to slow varying faults, so it's not very practical. The second method is much more universal. It is called the descriptor scheme. This one depends on the singular system. So there's the E matrix multiplied with the system. This E is a rectangle, and the A is rectangle. In this framework, you do not add any, and you do not add the font. You do not assume any dynamics of the font, so that you apply to the font of how it dynamics. However, you need to pay attention to the rank condition, which is crucial in the descriptor scheme. That is, the rank of E over the output matrix must be the dimension of the system. In this framework, we have two scheduling parameters rho, which are the control input, which is null, and the noble one is the sprung mass. So you add the sprung mass that you assume to be null as the scaling parameter. So our method can be summarized as follows. Because we arrive at this descriptor system, whereas the C matrix depends on the scaling parameter rho, you want to make it independent of rho in order to use the polytopic method later. So you want to add a filter to this output. And then you parameterize this observer. That means you express them as a function of some matrix variables to solve for. And then you solve some LMIs formed following the polytopic and grid-based method for the observer gain. And lastly, to evaluate your observers in both the frequency and the time domain. Now, first you want to add a filter to the output of the system. Why? Because you want to use later the polytopic method, and for that you need a parameter independent output matrix. However, you are restricted with the rank condition, so you cannot add too much to the system dynamics. And so we discovered that you can only filter the first components of the measurement. So there are two measurements, which are the accelerations of the two masses, and you can only filter the first one, or else it will violate the rank conditions. And by adding this filter and by designing an observer for this extended system, you have a C matrix that is parameter independent. And so you are now ready for the polytopic method. And now you need to solve for the observer matrices. So this is the structure of the observer, where you have N, J, H, R, and S, which are unknown matrices that you need to solve for. You also have the same nonlinearity in the system. The output you use is the filtered one. And when you use this observer, you need to perform, you need to satisfy some decoupling conditions. So basically, these three conditions that the observer matrices have to follow. And if you satisfy this, then the error dynamics is reduced to the following. So this is some A, and E is the estimation error. So it is the real state minus the estimate, which includes the fault. So you want to stabilize this system and mitigate the effect of omega, which consists of the disturbance and the noise, while you have some non-linearity that are lifted. So I will not detail the parameterization steps, but basically you solve the range conditions, the decoupling conditions that I just mentioned, and you arrive at the following form of the observer matrices. So all these 5 matrices are determined as soon as you find Z1 and Z2, which are the parameters. And with this, your error system becomes a system like this, where you have some nonlinearity and you have some noise where you want to attenuate. So the job is to find Z1 and Z2 to stabilize this one and attenuate the noise. So now we look at the polytopic method to solve for and implement the observer gains. So for this one, we solve the observer only at the vertices formed by the variation of rho. So rho varies and it forms a polytope, and you may only need to satisfy the atomize at the vertices of this polytope. In order to do this and to have a guaranteed rigorous proof of stability, you need to be affine in the parameters. And this method can be quite conservative. So in our paper, there's this theorem 1, which summarizes the polytopic method. So you solve this atomize and you obtain the Z1 and the Z2, and from this you get the observer's matrices in order to implement. And while you solve this, you minimize gamma 2, and by doing this, you optimize the H infinity norm of the error, and you mitigate the effect of the noise and disturbances. This is the board plot of the error system when you solve for the observer using the polytopic method. This one corresponds to only the font estimation part of the error. So this is the real font minus the estimated font. And you want to look at the transfer from the rho profile derivative, which is a disturbance, to this error. So there are 4 lines corresponding to 4 vertices formed by the variation of 2 parameters. So recall that the first one is the control inputs, and the second one is the sprung mass that you assume to be measured. So these form a polytope of 4 vertices, and you obtain at the 4 corners for both plots. And you see that the attenuation level is quite good at minus 50 decibel. This is the first scenario of simulation that we performed in order to validate our observer. So in this one, the road profile is a sinusoidal one. The mass of the vehicle is assumed to be constant throughout the time simulation, and the controller also stays constant. And we assume that the form of the system increases from 10% of the damper force to 50% of the damper force at 5 seconds. So here the force suddenly goes up. And from our result, we can see that the font estimation performance is quite good. Then there is a second simulation where we use an ISO type C board profile. We let the mass to vary at 3 seconds. So at this time, the mass goes up, and the controller is a switching one, it's a sky hook. controller. And the font, we assume that at 7 seconds, it increases from 20% to 40%. And from our simulation result, we can now see that the estimation result is also quite good. We also propose a method to solve for the observer gain using the grid-based design. So in order to do this, you still solve LMIs, but you solve them only at the grid points taken in the polytope and not at the vertices of the polytope. So in the polytope, you divide them into the grid points and you solve them. You satisfy the LMI at a high enough number of points taken inside. So there is no proof of stability. And it should work if you have enough points, but this is not proven. And you do not need to be affine in the parameters in order to do this. You're less conservative and the attenuation can be better than the polytopic one. However, you need to guarantee that the variation rate of the parameters is bounded, and which is something the polytopic method doesn't require. So there's this second theorem in our paper where we propose the LMI in the grid-based method. So it looks quite similar to the polytopic one. You still optimize the H infinity norm by minimizing this gamma. However, now you have a parameter dependent Lyapunov function. So this X matrix depends on the parameter. And you need to bound the rate of variation of the parameters in time. And you solve these LMIs at the grid points and not at the polytope of the, not at the vertices of the polytope. Here are the both plots of the error, so still the same error, the transfer from the disturbance to the font estimation error. And there are 25 lines corresponding to 25 frozen grid points. And you see that the attenuation level is much better than the polytopic method because now it is minus 100 decibel instead of minus 50. However, we didn't perform time simulation because there is a violation of the boundedness of the range of the scaling parameters when we use the Skype controller. So in summary, this work proposed font estimation schemes for the semi-active vehicle suspension. The novelty is that we consider a descriptor model that makes no assumption on the font dynamics, and we consider a sprung mass as varying, so we have a practical design, and we also propose two different methods for solving the gain, which are the polytopic one and the grid-based one. And our future work is to consider some uncertainty in the system for an even more robust design, because for now we have considered a perfectly normal model without any uncertainty. So thank you for your attention, and if you have any questions, feel free to contact me at this email.
I think it was a pretty interesting presentation, very theoretical. If you have any question, you can reach Mr. Tran, sorry, at that email address. I think we can move to the next presentation, which is titled On the Problem of Onboard Risk Assessment for Railway Hunting, presented by Kyriakos Kyritikakos from the University of Bari.
Thank you very much. I'm Spilios Vassos, yeah, okay. Sorry. It's okay. Oh, okay. Just one moment so I can find the slides here. you know how to do it full screen here? It's Italian to me. I don't recall the shortcut.
Control.
Okay, great. Thanks a lot.
No problem.
Okay. So good afternoon, ladies and gentlemen. I'm Spilios Fassois from the University of Patras in Greece. Kyriakos is the first author of this work, and he should be here to present it. He's finishing up his PhD. He could not make it, but you know, I'm going to present for him. And the other author is John Sakellariou, who is also collaborating on this project. We're with the Stochastic Mechanical Systems and Automation Laboratory at the University of Patras in Greece. The work, the title, it was announced just a few moments ago, but just to repeat it, essentially we're looking at on-board risk assessment for railway handling. And this is a series of studies that we're working on. This is a first exploratory study that I'm going to present. Let me get also the pointer here. Okay, and we can move on. Let's see, does this work or not? Yes. Okay, so here's an outline of the presentation. I'll start with a short introduction, the study goal, exactly what we're trying to do. Then I will talk a little bit about the simulation model, and then I will discuss the approach that we are proposing. I'm sorry. What happened here? Sorry. Yeah. I pressed something that I should not, I guess. Let's see. Do it very quickly, yeah. Page up, page down. Okay. So I will present the approach then, which is section number 4 here. And then I will talk about performance assessment and finally some concluding remarks. So maybe it's safer to do it here. Let's move on to the problem we're looking at. We're looking at handling. Why we're looking at handling? Because we are interested, of course, in safety. Primary consideration is safety, of course. And secondary is the ride comfort, of course, and also to prolong the rolling stock life. So what exactly is handling? Handling, you can see here a schematic representation, but I can tell you that it's a coupled lateral and yaw limit cycle oscillation of the vehicle. So a train, a railway vehicle will go like this, and we have a limit cycle operation that can occur. Okay, so this is the problem we are looking at, the larger problem. And this is how it happens, roughly speaking. So if we put speed, vehicle speed on this axis, and here we have the displacement of the vibration, of the oscillation, then for slow speeds, as we increase the speed linearly, for slow speed, you see this is the vibration, the lateral vibration of the vehicle, which is quite small. It's random and quite small vibration, no problem. But as we increase the speed, then we see that the oscillation amplitude will increase, and finally we enter handing here. So we have a limit cycle oscillation that is physically limited by the rails. Okay, so now in order for this to happen, we have to increase the speed because beyond a certain limit. There is a lower limit, a critical speed, below which no handling will occur. If we go past that critical speed, then handling may occur, but it depends not only on the velocity, but also on the condition of the rail and also the condition of the vehicle itself. So it's a little bit complicated problem because it depends on all these factors, not only on velocity. Okay, so what is the idea here? What are we trying to do? we are trying to have a vehicle that will be instrumented with accelerometers so that we can measure the vibration in different directions. And based on the measured signals, then we will be able to assess the risk that we run into of running into handing. So we know at any time instant whether handing is an issue or we're far away from handing and no problem, or whether we're approaching handing. So we want to be able to be alert. As soon as we approach handing, we want to know it. Right now, there are methods that will tell you that handing has just started. So there are methods for detecting handing once it has occurred. We're not looking into this. We're looking at being able to assess the risk of running into handing before it actually happens. So this is the idea, or very early, at a very early stage. So this is the idea in brief. Let's move on. Okay, so as I said, there are methods that are trying to do detection of handing, but of course, as I said, we're looking at risk assessment for handing. Okay, here is the idea of the critical speed. So if we run, this is the speed here, the vehicle speed, the axis represents the vehicle speed. So for low speeds, nothing happens. We have a stable motion. Then if we go beyond the critical speed, then there is a possibility for handing to occur, and actual handing will occur when the speed of the vehicle will reach the handing speed, which, as I said, depends not only on the condition of the vehicle, but also on the condition of the rail itself. So this is what we're trying to do. Okay, let's see on how this can be done. One possibility, of course, because handing is associated with a large vibration, would be to look at the level of the vibration. Okay, so if we have large vibration, then we would say that, you know, this is handing. But this is not a good indication, because we can have significant and large vibration even without handing if the quality of the rail is deteriorated or the vehicle has some kind of problems. Okay? So for this reason, we cannot just look at the vibration, the level of vibration. We have to look at some dynamic quantities. And the idea that we have followed in this work is the following. The idea is to to measure the signals in real time by using accelerometers, as I said, in different directions, and then develop a wheel set gray model, which will be updated, re-estimated at every time instant. And then based on that model, which will be nonlinear, then we compute the Lyapunov exponents. Actually, we need the maximum Lyapunov exponent. And based on that Lyapunov exponent, we can assess the risk of handing. This is the idea. Okay, so we start here with the model, the physical model that we have developed for the simulations. So for the simulations, we have developed a model, as you can see here, for one axle. It's a 2 degree of freedom model. We have the yaw angle, and also we have the lateral displacement, the lateral vibration. And there are certain assumptions. I will not go into the details of this, obviously, but just to mention that we assume rigidity, we assume linearity for the spring and damping elements. And also we assume that the excitation that we have is coming from the alignment track regularity that is designated as UA here. So UA is these are the rails, okay, left rail, let's say, right rail and left rail, and UA is this displacement in the alignment track regularity. So this is assuming to be a random process, and actually it follows standard standards. It has a specific power spectral density and so forth according to the standards. Then one develops the equation of motion, and so one will have Newton's law applied, and then we have suspension forces, we have creep forces, and we have normal contact forces. and because of this and the geometry, we're getting nonlinearities. So the actual simulation model is a nonlinear model, okay? We have nonlinearity. Okay, here are some more details about the geometry, the geometrical parameters, the excitation that I mentioned. And what we see here, if we do all the mathematical development applying Newton's law, which is nothing new here, it's quite simple actually, but applying all this, one will see that we have nonlinear and non-smooth functions of this quantity. Y is the lateral excursion, the lateral displacement, and UA is the alignment track irregularity, the excitation that I mentioned before, which UA is of course unknown, okay? UA is unknown. Okay, so here is the proposed methodology. What we'll propose is to put sensors, as you can see here. So we have 5 sensors. You see 1, 2, 3, 4, 5 accelerometers. So we measure acceleration at any time instant. And from these measurements, we can then obtain which are the measurements are Y1, X2, X3, Z4, Z5. Then very simply, we can obtain these quantities, and then we can integrate and obtain displacements and velocities. So from accelerations, we can integrate, obtain whatever we need, as mentioned. And then we develop a gray model of the wheel set, set. The gray model is shown here. It's basically a simplified model, a simplified version of the model that we used in the simulation. So in order to come up with this kind of model, we do certain simplifications. Okay, so we do a polynomial approximation of certain nonlinearities, and we make certain simplifications in order to come up with a simple model. This simple model has the characteristic that it is linear in the parameters, so you see the parameters in blue, but we have UA, which is unknown here and over there, and of course we have a cubic term over there. So the idea is the following, that for model estimation, in order to estimate this model and then use it in order to compute the Lyapunov exponent, we will somehow approximate UA, so we will get an approximate estimate, an approximate value of UA based on the sensor signals. Okay, so this is the idea. Once we do this, then it's very simple to estimate this model by using recursive least squares. With a forgetting factor, the usual technique, there's nothing, of course, this is very well known for many years. So one can do it either simultaneously for the 2 equations, or you can do it, or one can do it separately for each equation. Well, the result is very similar, and one can understand why this happens. So I won't go into the details here, but this is the recursive least squares estimation. Here we did it separately for the 2 equations, but it can be combined, of course. Okay, and let's move on. Now, the way that we have to approximate UA, I said, which is the actual excitation, in order to do the recursive least squares estimation of our model, the updating of our model, is based on geometrical conditions. And essentially, we assume no wheel lift, no lift of the wheel. And then based on the geometry, we get some expressions over here, and we're using these expressions in order to approximate UA. So we approximate UA based on these measurements that we already have, and the velocity of the vehicle, which is also measured. So we need to know the velocity of the vehicle at any time instant, right? Okay, so once this is known, then we take this back into our gray model, and then we can run our estimator and so forth. Now, there are some issues here in the denominator, and we're getting some peaks in the estimate. You see here the real value is in yellow, or actually orange. And then we have approximated in blue, and you see some spikes that come up. These are because of anomalies, you know, the small denominator and so forth. So what we're doing here, in order to avoid the spikes, is we're using a very simple median filter. One can use other types of filter as well, and filter out these spikes. So we have no issues with those. Okay, once this is done, then we go into the computation of the Lyapunov exponent. So, just to imagine about it, when you have a nonlinear system, which is an autonomous system, then we assume here that we're given a small initial displacement, a small initial deformation in our system, and then we let this evolve over time. And the question is whether this distance between the perturbation from the initial position, this is the perturbation that we're given, if this perturbation is increasing or decreasing or remains constant. If this perturbation, after some time, is decreasing, this means that we have a stable system, basically. And corresponding to a periodic motion, like a limit cycle that we have in Hunter, then this perturbation will not increase or decrease with time. It will remain approximately constant, okay? And this corresponds to a zero Lyapunov exponent, a maximum Lyapunov exponent that is equal to 0. So the whole idea is to compute that Lyapunov exponent. So for this to happen, we take our system and we put it in state space. You see the selection here of state variables. Now we take this approximation of the excitation that we put it in here, we do all the substitution, and we come with a nonlinear model because of this UA primarily, okay? And then the standard procedure to follow is to take the equations in state space, linearize, and use the Jacobian matrix in order to compute the maximum Lyapunov exponent. Okay, so here is a summary of the technique that we're proposing, the method that we're proposing. Very briefly, I will say that we start with the sensors, and then we do the numerical integration. As I explained, we approximate the uncertainty in the excitation, we remove the spikes, then we do the recursive least squares for updating the coefficients of the symbol model, and then based on the state space representation that I explained, we will compute the maximum Lyapunov exponent. And we will check to see whether we're close to 0. If we're close to 0, then we're approaching a limit cycle, so we're approaching Handin. Otherwise, we should be below 0. Okay, so here are some simulations. We have run many simulations, and V8 is the Handin speed, which changes according to the vehicle and according to the rail, as I said. So here we have different types of rail conditions, one nominal, one slightly worn, another is heavily worn. And so the Handin speed can vary. Here it varies as much as you can see, but also it depends upon the vehicle condition, right? And then we do simulations with different speeds, and we want to see whether we will get the right warning when we approach Handin. This is a typical signal, actually some typical signals from different rail profiles, as I mentioned before. Okay, here is an example. Here there is no Handin. The vehicle speed is at 205 meters per second, and you see the lateral acceleration, so we see just one signal here, right? Lateral acceleration, and we apply the procedure and we compute the maximum Lyapunov exponent. You see that we're below minus 0.4, so we're not approaching 0, and this means that we're safe, we're not close to Handin, okay? This is just one example. So we've run many examples like this, and I have a summary table to show you how the method performs. So here, for different time instants, we're doing 150 test cases. For each time instant, we're doing 150 test cases. Each time instant with 3 different rail conditions, 5 different speeds, and 10 simulations per speed. So we have a lot of simulations in order to get some reliable results, okay? And here you see the maximum Lyapunov exponent. Now, in these cases, designated by green, you see the mean value and then upper and lower bounds of the estimated Lyapunov exponents. You see, with green, we're not close to Handin in reality. These are the actual these are the actual values. So we're far from hand-in, and if you use here this area to designate low risk of hand-in, this is a moderate risk of hand-in when we approach 0 or go just a bit above it, which can happen for errors, etc., and other factors. Then here we have a moderate risk, and as soon as we go above a certain limit, then of course we have a high risk. So if you see, the actual low-risk cases are correctly designated as low risk here. So this is what the method predicts. The method says that in these cases, in all these cases, you don't have a considerable risk, which is correct. And then as soon as we come closer to hand-in, then we have a moderate risk, which is correctly predicted as being moderate risk. And then as soon as we go, at hand-in basically, then we have a high risk, and this is properly designated when we come very close actually to hand-in. So these are summary results, and I have a confusion matrix here. So these are the true class, low risk, moderate risk, high risk, according to the actual occurrence of hand-in. And on the horizontal axis, we have the predicted class. So you can see that we're on the diagonal for most cases, and we just have a few cases that are off the diagonal. So it means that we can correctly, with good accuracy, the overall accuracy is at about 90%. So with an accuracy of about 90%, we can predict hand-in real time. Of course, now these are results that go back a few months ago. Now we have improved it. We're at an accuracy level which is much higher than this, around 96 to 97%. We're going to be publishing this work, of course. And also we're doing simulations with a SIMPAC, a very detailed simulation model that has the whole railway vehicle, not only part of it, but the whole vehicle. So we have very reliable simulations, and perhaps we'll be able to get some experimental data as well and confirm these results also experimentally. So these are the developments and where we stand. So just to summarize very quickly, we looked at the problem of railway hand-in assessment, risk assessment. We presented a novel method that is based on a wheel-set gray model, recursively squares, very simple, and maximum Lyapunov exponent estimation. And the performance has been examined systematically via 1,500 numerical experiments and 3 different track conditions. The results indicated, as we saw, an effective accuracy, classification accuracy of 90% here. And the study has been concept proven so far, and as I mentioned, further work is going on, and we're going to be presenting some new results a little bit later on. With this, thank you very much for your attention. If there are any questions, I will be happy to try to answer. Thank you very much.
Thank you very much for the nice presentation. Is there any question? We have only time for one short question.
Okay. Thank you for your presentation, teacher. I have 2 quick questions. First one, in slide 9, you show 5 sensors. You installed the sensors only one shaft in one wagon?
Right. These are 5 sensors on the shaft, but you don't need to put them on every shaft. For one vehicle, the plan is to have them on one shaft. So it will be 5 sensors per vehicle.
Okay, it's my second question.
Yes.
You answered. Thank you.
Thank you.
Thank you very much for the presentation again. We have to move.
Thank you very much.
Thank you very much for the next presentation. Before moving to the next presentation, let me introduce my co-chair of the session, Mogens Blake from the University of Denmark. He's going to serve as a chair for the last 2 papers.
Thank you very much, Daniel. I would like to ask the next speaker to come to the floor. We are going to hear about SAFE and fault tolerant control of industrial differential drive. And you are Vitor? Yeah, so Vitor Andrea will present the paper. The floor is yours. Thank you.
Good afternoon to everyone. Happy to be here. Thank you to the organizer. Thank you to all of you to attend to this section. As I already said, I'm Vito Andrea Racanelli, a PhD student from Politecnico di Bari, and today I'm going to present you our works titled Safe and Fault-Tolerant Control of Industrial Differential Drive Vehicles, which I made with Professor Saverio Mascolo. Let's start with the motivation of this work and some consideration. First of all, a lot of manufacturing industries, even logistic industries, use vehicles to move loads in their warehouses. And some of these vehicles can, depending on the use of them, can start from hundreds of kilograms and then grew to more than 10 tons of kilograms. So depending on the weights of these vehicles, they can cause a lot of damages. If we think about economical damages, imagine a vehicle like this that loses control inside a warehouse, and even some fatalities if we think about operators and workers inside the factory. And these vehicles need to move correctly inside these warehouses. In fact, mainly these vehicles tend to have a speed controller to act correctly. We have considered just a particular category of these vehicles, and these are the differential drive vehicles. We can think about them like a forklift, for example, where each wheel works independently. They have two motors, and due to the difference of speed of these two motors, they are free to move forward, backward, and turning, pivot, and so on. Of course, for these vehicles, for the maneuverability, it's necessary to have an encoder for controlling the speed of each motor. And in case we have some fault encoder, we can have some serious accident. And this is more evident for differential drive vehicles than other, because in differential drive vehicles, due to their kinematics, they tend to turn in case of a fault instantaneously. We can see here an example video where in a moment an accident could happen. And even if usually these vehicles are equipped with the famous big red button to push, the international law, for example, if we think about the European Directive number 42 of 2006, doesn't consider them inside the loop, the safety loop. So we thought about something that can improve the safety of this vehicle. So someone of you can talk me and say, okay, let's try to replicate this encoder. Let's put two encoders to ensure safety. Yes, but sometimes the encoder redundancy is not possible. Maybe for high cost of this sensor or the space inside the motor, the shaft where you can place it. So someone of you can think also, okay, let's put some safety encoder. We know that this regulation, international regulation, treat them with the safety integrity level for the classify them how a sensor or an actuator and so on is safe. We start from seal 1 and we go to seal 4 that is the most safe sensor. But these sensors sometimes cost a lot, and due to their form, they cannot be mounted on every vehicles. So we start to think about the classical encoder that are common in industries, the not safe one. So we thought about incremental encoder. For who of you doesn't know incremental encoder, this encoder measure the differences, measure the speed of the shaft that is rotating due to some signal. This signal is a square wave. In this case, we see a signal. We see channel A as channel B. This is for a quadrature encoder. We call them quadrature because each of these channels is shifted 90 degrees with respect of the other. And sorry. And measuring the time that intercure between each one of these edges, we can measure the speed, okay? And measuring the difference with the other channel, we can also detect the direction of the motor. So we can know if the motor is running clockwise or counterclockwise. We can measure the number of edges in a period using this equation. So the number of edges on the channel A, for example, is the sum in a period of time, delta t, that is measured in this way. So it is the difference between this sampling and the previous sampling, all divided by the tension of the encoder. So VGH is the tension on the channel A, for example. So we can measure the number of edges. And using this, we can also get the measured speed for each channel. So the rotational speed is measured in this way. So we have 2p over 4 ppr. ppr is pulse per revolution that classify the resolution that each encoder sensor. We can start from a few hundred to go to few thousands, multiplied by the number of edges detected over the period of time. I made this premise before introducing you the fault scenarios. And the fault scenarios that considered in our work could be the encoder detachment that has a very high severity, where the encoder detached from the shaft, but has a low occurrency. The encoder stuck means that the measurement of the encoder stop in some point. Also, this has a very high severity and a medium occurrency. And also generic encoder failure. That can be some electrical problem or something like that. We consider this with high severity but low occurrency. And also we consider not only the encoder, so the sensor in our work, but also part of the actuator, in this case the power driver. We can have, for example, some shorts on the driver that has also a very high severity, but very low occurrency, if they are designed well, of course. or maybe even the driver can broke. Low severity and low occurrency. These are our fault scenarios. And we defined also some safety requirements for our control system. First of all, we wanted to have a detection in time. So we wanted that the detection time was at least smaller than 50 times the sampling time. In our experiment, this sampling time was 0.01 seconds. We want to avoid, of course, fault detection. If we cannot, we would like to keep them lower as possible because it will become unusable for the operator. We want to detect all the faults, so we don't want to miss some detection. And we want to define a safe state behavior, so in case of failure, how the control system would act. Given these premises, we divided our work into steps. A first step is a start test, so a way of testing the encoder before the start of the machine itself. And this test starts from this intuition. If we consider that every motor in industrial vehicles is equipped with gears, we can use the space between each one of these gears, known as backlash, and move the motor just for that amount of space. And what happens? The motors move, but cannot transmit force to the passive gear, so the system is still safe. In this case, for example, if we do a start test and we start clockwise, we have this gap, and we can exploit it for our test. Let's say that, for example, we wanted to start counterclockwise. In this case, the gear is already pushed against the passive gear. We cannot exploit that, so we need to do in the opposite direction. So the test is repeated in case 2 times, and then it's aborted if failed. In this period, of course, we will have the signal of the encoder, and we will do a logical XOR of the signal of the encoder. That now I will show you why we do that. Because we have to, on the start test, to verify some condition. The first one, we have that the number of edges on the channel A should be the same on the channel B. We include this term to avoid odd count of the edges, because it could happen that maybe we didn't pass all the period. That the measured speed on the channel A is the same on the channel B, that is defined the real speed, rotational speed. And of course, that the rotational speed on the signal of A XOR B should be twice the speed. And this is the proposed state machine. We started from idle, so if the command is operated, we go to the armed state. If the test is passed, we go to the moving state. Then, in the moving state, if commands are released, we go back to the idle. In moving state, if a fail is detected, that this is maybe is done maybe measuring the residual. We go to the fail-safe state, where the brakes are put on. In the armed state, that was the previous one, if the test fails, the command, it goes to the fail state, and the command released goes to idle. In our experiment, we use, this was an experiment set up with the two 24-volt DC motor equipped with the old encoder, and we used a custom board. And we have done experiment with fault injection. In this experiment, this was the trajectory that we choose because can explore all the movement, and this was the signal. On conclusion, due to this operating principle of the system, we designed this controller, safe controller for differential encoders. For absolute encoder, the control algorithm works with minor changes, and we have shown the effectiveness of this fault detection system in presence of component faults. Thank you for attention. Sorry for being so long.
No, I think you started a bit late, but now we have time for one question. Yes, please.
Just a small observation first. When you say industrial vehicles, why not to use other sensors? For example, a LiDAR, a camera, in order to estimate the pose.
Sorry, you said which kind of
You
sensor?
say industrial sensor, industrial vehicles, no?
Yes.
Industrial vehicles, usually we have another sensors like a LiDAR, like a camera, in order to estimate the pose with a sensor fusion algorithm. I say this is interesting for you to see. But also, in this experimental test you use, I don't see any load on the vehicle. So how this can affect the estimation?
Okay, thank you for the question. For the first part of the question, we didn't use a LiDAR sensor, camera sensor, because, of course, they have some problems that we cannot avoid. For example, optical problem. In presence of dirt on this sensor, we cannot measure the environment and do pose estimation. For the second part, what you asked, sorry? With the load, okay. We consider, okay, I didn't maybe explain it well because we considered the model of the system, and in the model we considered the system with the empty load and the maximum load, because Low's regulation guarantees only a maximum load. So between this range, our estimation used to work.
I have an extremely brief question. Which safety level, you know, the IEC safety levels, which safety level is such a vehicle approved for?
In this case, we are going to try to certify this for SIL 2. Safety level SIL 2.
Safety level
That
2.
is, I think, the same as performance level C, if I have a good memory with the lows.
Yes, yes. Okay. Well, let us thank the speaker.
Thank you.
The last but not least presentation in this session is towards enhancing security in intelligent transportation, a simulation-based approach. And it will be presented by Marcelo Agustino Mangini from University of Bari. The microphone is a blue one on the table. Please, Marcelo.
Okay. Thank you, Chair, for the presentation. This work was developed with Aragon Institute with the collaboration of Aragon Institute for Engineering Research, precisely Jorge Holvetz and Christian Maria, and we, with my colleague Wasim Ali and Maria Piafanti of the Polytechnic of Bari. The idea is to propose a simulation-based approach in order to enhance security in intelligent transportation system. Okay. Indeed, today we have the possibility to introduce in intelligent transportation systems communication network. We can use VANET in order to facilitate vehicle-to-vehicle and vehicle-to-infrastructure communication. Moreover, in VANETs, each vehicle is both a wireless receiver and a transmitter, sending data to nearby vehicles or infrastructure. VANET is important because it improves the safety in urban mobility. In fact, the communication network enhances road safety and traffic efficiency. For example, it is possible to send a message about the occurrence of an accident or traffic condition data information. But in this case, an intelligent transportation systems becomes a cyber-physical system in which vehicles and infrastructure send message, information, data. And so it is possible to attack this system. Now, an encryption technique protects the integrity and confidentiality of the data, and while authentication mechanisms validate the identities of participants. However, an intruder can enter in the system with a stolen identity and can inject in the system malicious messages. In this context, a simulation tool can be important to generate a big data set. And it is important to use this big data set for training machine learning technique in order to detect the intrusion. For this reason, these one are the objective of this paper. We want to integrate traffic and network simulation tools. We simulate VANET communication protocols, including wave standards, is a protocol, a wireless protocol used in transportation systems, and analyzing message exchanges in order to detect intrusion. Then we want to implement a robust VANET framework that can be used as a point of reference for the machine learning techniques. In this slide, you can note a VANET scenario. We have a road traffic system in which we have vehicles and infrastructure. The infrastructure are antennas. And it is important for the safety. The communication network, the VANET, is important for the safety of this system. But it is necessary to analyze common threats and attack on this communication network. Wave is the protocol, is the wireless protocol used in realistic scenarios of transportation systems. This protocol uses three types of messages: basic safety message that include basic information about vehicles, such as identification, route, location, etc. And these messages are sent periodically. On the contrary, we have a wave shorted message that include road conditions and request. For example, a driver can request a route, or the vehicle can request authentication certificates. And then the last type of message is the wave service advertisement that are not only service advertisement as the availability of a parking or a commercial purpose and so on, but also alerting in some cases, for example, warning for an accident or warning for a traffic congestion. This one is the framework for our simulation. We have used the VANES framework. This one is an open source software, and using VANES, it is possible to integrate together Sumo, that is another open source software, and Omnet++. Another open source software. We have used naturally open source software in which it is possible to include program in C++. So we have two, in this framework, we have two software, one for the road traffic systems, modeling, and the other one for the wireless network simulation. And both simulators are bidirectionally coupled. So we have put in Omnet++, that is the network communication software, the demo, this one, Tracy demo 11p.h, that is a demo of VANES, in order to include in Omnet++ the wave protocol. In fact, we have the three possible messages, WSM, WSA, and BSM, that are the three types of message. Then we have included in Omnet the parameters of the system. For example, we can note the maximum distance between two objects in order to have a communication, and or the location of some nodes or acre in this case. The acre are the intruder for the intelligent transportation systems. And then, in this way, we have performed a simulation, and we have simulated a real case study, a scenario from Bologna, in a particular area, Pasubio area, during the city peak traffic hour, and the time interval is 8-9 a.m. In this time interval, we have 3,700 vehicles, standard vehicles, but we want to adapt this scenario to autonomous vehicles, and so we have scaled this scenario to 500 number of vehicles that circulates in this area. Then we have introduced two types of attack. The attack in red and the attack in blue. The attack in red sends false alerts about an accident in a specific location, in particular near to a charging station. The aim is that the other autonomous vehicle go to another charging station because there is an accident near the specific charging station that is avoided from using this attack. And the second attack is, on the contrary, is a denial of service attack that is the aim to make unavailable the resources, the communication resources, and so in this case the antennas. We have two screenshots of this simulation. In the first, regarding the first attack, the node 3 that correspond to the attacker 1 send to the nearby nodes the message regarding the accidents. On the contrary, in the second attack, there is the message are sent to the wall network. And after a running of 3,600 seconds, we were able to capture crucial data that includes the number of generated message for the first attack. Oh, sorry. For the first attack, does not work correctly. For the first attack, the WSA message. For the second attack, the W short message. And naturally, the denial of service attack create a great number of messages that are propagated both from hacker type 2, but then by hacker type 1. Yes. And finally, this framework can be the base for any other work with large-scale studies and for other work that wants to study, to implement machine learning techniques and can use the data that are generated by this simulation. These one are the results of the simulation. We have a lot of packets sent by the hacker type 2 because it's a denial of service attack. On the contrary, we have 840 messages sent by the attacker 1 that regards the presence of an accident near the charging station. And then we have the attacker 2 occupy a great quantity of the channel. On the contrary, the first attack is the channel is free, but the aim is different. The aim of the attacker 1 is different. The limitation of our work for now, due to the limited duration of our simulation and the number of vehicles involved, the simulation generated a small data set. So it is impossible to use this small data set with machine learning techniques, with the deep learning techniques, and so we have used only a threshold technique in order to detect these attacks, but naturally there are the number of vehicle is 500. Is we don't have a lot of vehicles. Then we can use a larger area, and then we can add other different traffic conditions to this scenario. But this one represents an idea to create a simulation tool in order to generate a great database, a big database, sorry. In conclusion, we developed and implemented a simulation framework that integrates the realistic traffic scenario of Sumo, in particular the Bologna model. We have used the Omnet Plus for the and veins for the communication network and protocols. We evaluated the impact of various attacks on VANETs, and in particular we simulated two different types of network attackers in the zone of Bologna, the Pasubio area. Okay.
I would like to invite one or two questions to the speaker. Well, I have a stupid one. What do I need the VA-net for in my car?
I don't know. No, sorry, the question, because I don't know.
No, okay. I was just asking a stupid question because this is not my area, but I have a car and it's highly automated. So what do I use or what does my car use the VA-net for?
If for a standard car, in this case, but now standard car are it is possible to connect standard car in transportation systems. So for this, in this particular system, we have simulate autonomous vehicle, but it is possible to include in this particular system other vehicles, our cars, that are in which it is possible to connect this, when it is possible to connect this car with the infrastructure. And so we can use the standard car in this simulation. Then the problem is the cars that are not connected, because in this case it is necessary to understand their behavior in the system.
So after this session, you might give me the code to ensure that I always have green light.
Green light, yeah.
Thank you very much to all the speakers and the chairman. The next thing is a coffee break that has just started.
Hello?
Yeah, it's okay, right? No, it's okay. So I was saying that we have a lot of noise, but it's time to start. Actually, we're a bit late. The schedule has been a bit tight, but it's okay. I hope more people will be joining us in a few minutes, but for the sake of time, I think it's preferable to start right now. So the first presentation will be given by Dr. Dennis, right? And it's entitled Safe Vehicle Motion Design with Learning for Moving in Environment and Uncertainties. And it's from Hungary, from the University Institute for Computer Science and Control in Hungary, right? In Budapest.
It's a computer science and automatization institute.
Yes, I understand. Computer Science and Automation Institute. Okay, so the floor is yours, please. You can start.
Okay. Good afternoon. My name is Dénes Tompos, and the paper I present today is the Safe Vehicle Motion Design with Learning for Moving in Environment with Uncertainties. Okay, so cooperation of drones and ground vehicles is a novel research trend in the field of automatic vehicle control, and also the delivery processes and item transportation can be facilitated via automated vehicles. And the goal of this paper is to introduce a safe trajectory design for indoor drones. The paper uses two algorithms in tandem to create a safe trajectory for the controlled vehicle and also optimize its trajectory. The two algorithms, one is a reinforcement learning-based algorithm. It's responsible for creating an optimal trajectory, and other algorithm is introduced, which is a supervisor responsible for the safe trajectory of the controlled vehicle. And also, these algorithms calculate the trajectory with the distances and velocities of the controlled vehicles from a possible collision area. And okay. So the algorithm was tested in simulations. The environment for the simulation is a 3 by 4 meter space, and two vehicles move in this space. One vehicle is a ground vehicle, a mobile robot or a car, which it takes lapses in an ellipsis form of trajectory. And the other is the controlled vehicle, which is a drone. It has a three-dimensional pathway, and it's designed in a way so it crosses the pathway of the moving mobile robot in the simulation. Also, the simulation handles the moving vehicles point-like objects. However, the physical size is considered with added safe distance to their position. Yeah. And so to calculate these conflict zones, these calculations can be done in an offline process outside of the simulation. It consists of the following steps. The space coordinated occupied by both, possibly occupied by both vehicles, was selected, and they were separated into clusters via Cummins clustering algorithms, and the outlier points was cut out with the help of the Mahalanobis distance. And these clusters were used in so these separated clusters was used in the simulation as possible conflict zones or collision zones. Okay. And and in the simulation, one of the closest collision zone is considered as the next possible conflict situation. In this collision zone, its mean is considered as its center, and the distances of the vehicles was calculated from this center point. Also, since the cluster creating this collision zone is not necessarily uniform, a separate safe distance was determined from its center point for each vehicle. And yeah. Okay. So these are the parameters that the algorithms work with. The first algorithm is a reinforcement learn-based algorithm. The algorithm itself consists of two neural networks. One is an actor network, is responsible for generating a control signal from the observations. And the second neural network is a critic network, which is responsible for adjusting the actor network based on the reward collected from the environment. This reward is an arbitrary function created by the user. In this case of the simulation, it consists of the distance traveled by the drone minus the absolute acceleration and minus the penalty in case of collision with the controlled objects. Yes. And the other control algorithm is the supervisor. Its goal is to minimize the energy needed to avoid collision with the disturbance. And this energy defined as the delta change of acceleration in the simulation. And quadratic optimization was used to calculate this optimal value, and with a constraint that it cannot enter, so both vehicles cannot be in the safe zone determined by the safe distances at the same time, which would mean a collision from within the two vehicles. Yeah, so this is the reward collected via the reinforcement learning algorithm during the simulations. This is the velocity function of the drone. it shows that in conflict situation the drone stops or either slows down, so it avoids collision with the moving disturbance. And here are the illustrations of the trajectories during the simulation. The left side is a spiral kind of shape. It's the X and Y plane plotted for each time instances, and the projections of the moving vehicles in the simulation are viewed on the plane, and it shows the avoiding, so as the drone avoids the conflict situation. Yeah. And on the right side is created with the distances, so it's it's more visible in another coordinate system. So the own coordinate system created by the distances shows that the two vehicles trajectory doesn't enter in the determined conflict zone at the same time. And so, in summary, an algorithm was created to generate conflict zones from the predefined pathways, and a safe motion of a drone within this environment was guaranteed, and the drone is continuously adapting to the mobile vehicle movement in the conflict zone. And for future plans, currently the reinforcement learning algorithm signal is suboptimal, which means it only uses the maximum and the minimum allowed output for control, and is probably due to the weight in the reward function, which will be solved with giving a higher value to the acceleration penalty. Thank you for your attention.
Thank you very much for the presentation. Are there any questions or comments that anybody would like to make on this presentation? Maybe a brief question. What about warranties? You said that there can be warranties, that there will be no collision. Is this something warranted? Mathematically, we know that, or not?
Yes, it's so. The signal is created.
To use the micro, please. If you want to use
the supervisor, so the necessary acceleration calculated via the supervisor and the reinforcement learning algorithm. And so the supervisor's signal has some kind of priority, and it's always be a safe motion. However, in a range, the reinforcement learning algorithm can change this signal to be more optimal.
Okay. I understand. Okay. What about extending this to more vehicles, UAVs, vehicles, etc.? Is this something easily extendable?
Relatively, yes.
Oh,
so because of the quadratic optimization, I just have to add more constraints, sorry. And the reinforcement learning algorithm, I have to do a new training session, but extra signals can be added.
I understand. Okay, very good. Thank you very much. Any further questions or comments for our presenter? Okay, if not, thank you very much again.
Thank you.
And I would like to ask if we have the second presenter, the presenter of the second paper with us here today. You're right here. Okay, great. Okay, thank you. Yes.
It's the full screen mode. I want to present. This one? Control no.
Control what is it? Control L. Control L. Okay. Control L. Okay.
Okay,
Thanks a lot. Yeah. Okay. So.
Okay.
So just one moment to introduce you, to introduce the presentation. So we go on with the second paper in this session. The title of the second paper, as you can already see, is fault-tolerant control of a bio-inspired UAV using sliding mode. And it's going to be presented by Tian Lema, is that?
Yeah.
You? Okay, from university or what?
University of Exeter.
Okay, very good. So the floor is yours. Okay.
Oh?
The floor is yours, please. Go ahead.
Okay. Okay. So thanks for coming to my presentation. Today I will discuss about the fault tolerance control of the bio-inspired UAV using sliding mode. So in this presentation, I got three main parts. The first part is the brief introduction of bio-inspired UAV, and then the second part, I will introduce the sliding mode controller for a specific model, and of course, I will introduce the model itself. So finally, I will present the fault tolerance simulation result of the bio-inspired model controlled by my sliding mode control system. So let's start from the first part. So nowadays, a lot of paper referred about the aerodynamic structure and structure implementation of bio-inspired UAV, but there are only few people discussed about the control system, because in the nature, the bird doesn't have the vertical tail, so their flight control system is really different from the normal commercial aircraft using their non-conventional control surface. So in this paper, we designed a fault tolerance control system to use the multi-actuators, non-conventional actuators from the nature bird instead of the commercial aircraft. And then we will test its maneuverability, and we will also design the control system for the specific model, which will be introduced later, using its over-actuated system to control its maneuverability and test if the model itself the multi-actuator failed, if the control system can handle such type of failure. So these four figures from Howie's work. So the first two figures give a brief idea of the physical model. So this is the wooden ribbon model. The model is come from the ribbon in nature. And also, the Howie provide the engineering blueprints. So that's how we collect the data and derive our model itself from other software. So here, I present a table. We collect the information such as mass and chord length, and also the span from the engineering blueprints. And based on this information shown in the right-hand side, we derive the model and recreated in the AVR software, which is really important because we can collect the aerodynamic coefficients preparing for our nonlinear model simulation to the MATLAB and the Simulink. So the right-hand side shows the model itself from the AVR software. So as I introduced, this model created by Huawei, but the problem is the model doesn't have a propulsion system. So to modify the model itself, I added a propulsion system aligned in the y-axis, provide some thrust, and for increasing the longitudinal motion, the maneuverability, a very small inclined angle is applied to control its longitudinal motion. And so next part is the most important part, actuators. So this surface have 6 different actuators, 4 of them located on the main wing and the rest 2 of them located on the tail. Let me introduce it more detailed. So the first two figures show the inboard actuators attached on the main wing. So we call it flaps. These 2 actuators can move symmetrically or asymmetrically to control the system in both longitudinal and lateral motion. So when the flap moves asymmetrically, so the function is just like a rudder, or it's just like a rudder in the commercial aircraft, and it controls the lateral motion of the model. And when the flap moves symmetrically, so the function is just like an elevator. So in this case, it only controls the pitch motion of the aircraft. So in this case, these 2 actuators can simulate 4 different types of control surface comparing with the normal civil aircraft. So the aileron, the things become easier because the aileron attached on the outer side of the main wing. In this case, the aileron can only move asymmetrically. So the function of the aileron just the same as the aileron in commercial aircraft. So the tail is on the behind of the aircraft. So the tail is similar to the flap. It can move symmetrically or asymmetrically. So when the tail moves symmetrically, the function is same as elevator and control the pitch motion of the model. And when the tail moves asymmetrically, so it controls the lateral motion of the aircraft. So this is the 6 different actuators. For the control system part, it is a little bit tedious comparing with the model because there are a lot of equations, formulas. I will only highlight some of them, important principal equations, then I will move to the next part. So in the linear time variant systems, we split the states into 2 parts. So the first part is the longitudinal parts. We are looking for the x velocity, y velocity, pitch rate, and pitch angle. So in the lateral motion, we are looking for the y velocity, roll rate, yield rate, and roll angle, which showed in the equation 2 and 3. So W is quite important because this is the fault matrix. So when the W equals to 1 means this actuator is completely functional, and when W equals to 0 means in this case, the actuator is fully failed. So if W is between 0 and 1, that means the actuator is partly failed. So here, as I introduced before, there are total 6 actuators plus 1 thrust on the model, but we can simulate total 11 control surface. 5 of them control the longitudinal, and the best part of them control the lateral motion, which show in the equation 5 and 6. So as this system is the over-actuated system, we got 11 control surface, so we need to factorize the B matrix and get the new BV matrix, which present the virtual input to use the control allocation in this controller. And we can also find the B2, pseudo-inverse B2, which can help us to optimize the system and convert the virtual control signal back to our actual control signal. So these 2 equations is presented in equation 7 and equation 10. And then we also add another integral action tracking in these control systems. So in the integral action tracking, we need to create a new augmented system, which shown in the equation 14. So our new augmented system XA contains both XR, which called the tracking states, and the original states X. So XR has been given in equation 12. So the new augmented system has been presented in equation 15. So, and then to simplify these equations, we got a new equation 16, but these equations still contain the fault matrix. So to keep simplify this equation, we will need to define another called scaling of the virtual control input. So we can use this input to replace the most part of the controller here from equation 16. And in this case, the new controller will absorb the W matrix because this scaling of the virtual control input absorb the fault matrix W. So this equation 19 is fairly important because the sliding mode controller design is based on the equation 19. So here is the sliding mode controller design. So the S are design parameter which try to reduce the order, and as we can see the equation 25, assuming the controller can induce the ideal sliding motion on S, so the ideal reduced order sliding motion has been given in equation 25. So in this equation, we got the control law with linear parts and the nonlinear parts showing equation 26. So the nonlinear parts comes from the equation 27, and the linear parts comes from the equation 13. So in this controller design, I just highlight some important information. So if you want to learn some more information about that, you can read my conference or Christopher's the paper which presented here. Okay, now let's move back to the model design. So I already introduced this part. We split the states and also the input into longitudinal and lateral motion. So before doing the nonlinear simulation, I also find the open loop properties which showed eigenvalue tables on the right-hand side. All these poles are negative, means the whole system is stable in this case. And of course, on the right-hand side, the closed loop preventive properties show the all negative pole. Yeah. So for the trim conditions, I just follow the Howie's work. So he suggests that we use the angle of attack 10 degrees and velocity, true air velocity at roughly 6 meters per second. And in this case, the AV air gave the result. The deflection of the elevator is -1 degrees in this case. So there are 4 important cases to test the fault tolerance control system here. So the first case is the fault-free. So the matrix W is all 1, which means there's no actuator failure. And the case 2, 3, and 4 simulate the elevator fail, aileron fail, and even more severe actuator fail case, including the both flaps, left aileron and left elevator fail. In this case, 4 of 6 actuators failed. Let's see if we can handle this type of severe actuator failure. So this is just an example from the fault-free case. If we see the left-hand side of the figure, all actuators works well, no one fail. And if we see the right-hand side, in this case, all these commands can reach with very low latency and minimal overshoot. So the overall performance of the model at least reached our target. So we control the flat path angle, VTAS, roll, and side slip. But to avoiding the decoupling effects, we doing this command one by one. So we can see there's no any decoupling effects to affect the simulation result. So when the elevator fail case here, we can see 2 of 6 actuators fail. So but fortunately, elevator only affect a little bit about the lateral motion, so we just need to make the aileron move a little bit aggressive compared to the previous case to compensate it. So if we see the right-hand side, the elevator fail case here, all these commands can be reached still with a relatively low latency, and the performance does not affect it at all, to be honest. So for the aileron failure case, because aileron control the lateral motion, so actually the elevator will need to deflect a lot more aggressive compared to previous case. If we compare the previous case, the elevator 2 control surface here, it moved from 9.5 degree deflection increased to 7.5 to compensate the aileron fail. But fortunately, all the command can be reached still with very low latency and a small overshot. So that's great. So finally, this case is a very severe actuator failure case. 4 of 6 total actuators failed in this case. So if we see the actuator movement, we will see very aggressive actuator movement increase to up to -40 in elevator 2 to compensate the most of actuator failure. But fortunately, with a little bit performance reduced, it can still reach our target latency, target command with a little higher latency, but still with very small overshoot. So let me make the conclusion. We designed a sliding mode controller with fault tolerance sliding mode controller for the specific Raven 2 models, and we designed designed decoupling the denominator and the non-denominator states by designing the feedback gain, and finally we can see this type of controller has really good capabilities to dealing with the actuator fail, even up to 4 of 6 actuator fails. Thanks for listening to my presentation, and if you have any questions, you are free to ask.
Okay, thank you very much for the presentation. Interesting, very interesting. Any comments or questions from the audience, please? Yes, please.
Thank you very much for your presentation. Since you're using sliding modes to perform some sort of dynamic allocation, I suppose, of your actuators, yeah. Have you considered using the robustness of the sliding modes just as a passive fault-tolerant approach instead of doing reallocation?
This sliding mode controller system has the robustness, so I think in this design, the robustness test is, I think it should be handled the robustness test. So,
but I mean, you're considering complete failures of your actuators, which in reality, what would happen is that you will have some sort of difficult to compensate fault, and then you would shut down the actuator, right? So in that case, sliding mode maybe could also help just by doing passive fault tolerance. Have you considered something like that?
Sorry?
I'm thinking that in cases where you don't have a breakdown of your actuators, but you would shut them down yourself because of a severe fault, yeah. Could the robustness of the sliding mode component you have passively compensate for these faults and not having to shut them down?
Oh.
Without shutting down the sensors, the actuators?
No.
All the actuators, without shutting them down.
Yeah.
That's what he's asking. Yeah.
Without,
so in other words, yeah. you have some actuators that are faulty, right?
Yeah.
Now you shut them down, right?
Yes.
Stop, right?
Yes.
What if you don't stop them and you let the controller take care? Have you tried it? That's the question.
Oh, if I don't shut them down, that means there's no actuator failure in this case. So the control allocation will split the work to all these actuators and make sure the system is stable. So I just give this machine to the control allocation design in this way.
Okay. Yes. Thank you.
Okay, thank you. So I think that, well, really what he's asking is that you have to simulate the fault and let the simulation run with a faulty actuator and see what happens. But if I understood well, you did not do that. But maybe it's something for the future, right?
Okay.
If I understand well, yeah.
Okay.
Okay. Okay. Well, thank you very much again.
Thank you.
Now we have the next paper. The paper is entitled, let me see here, for just a moment, yeah. The paper is Modeling of Autonomous Vehicle Based on Multi-Scale Reduced Kernel Principal Component Analysis. We don't have the speaker here, but we play the video. So please bear with me for just a couple of minutes and I will start the video.
Everyone, I am Janet, Doctor in Electrical Engineering. I am excited to share my research on modeling autonomous vehicle. Everyone, multi-scale reduced kernel principal component analysis. My presentation today will be divided into 5 parts. I will begin by introduction, then I will introduce the model of autonomous vehicles, then I will present the model of multi-scale reduced principal component analysis. Also, I will present some results and discussion. Finally, I will finish with some conclusions. And now let's talk about why this research is important. There are some major issues with the road safety, traffic congestion, and environment impact. Also, human errors such as distracted driving and speeding causes some accident. Then conventional vehicles also contribute significantly to pollution and climate change. For these reasons, autonomous vehicles can help solve these problems. They have the potential to improve road safety, traffic efficiency, accessibility, environmental sustainability. So developing and using autonomous vehicles is essential for a safer, more efficient, and inclusive transportation systems. So the goal of this presentation is to model and estimate variables of autonomous vehicle using data-driven technique called multi-scale reduced kernel principal component analysis. Let's take a look at the key components of autonomous vehicles. As represented in this structure, the autonomous vehicles is composed of some sensors. This sensor aims to gather data from the environment. This includes GPS, radar, LiDAR, cameras. Also, it's composed of motion planning. This involves planning the vehicle's path and determining its acceleration to ensure smooth and efficient movement. Then it's composed of control system. The control system manages the vehicle's steering and braking, ensuring it follows the planned path accurately. Now let's move on to some key questions that are fundamental to our research. First, we have the question that represent the position coordinates. This question gives the vehicle's velocity coordinates. Following that, there is an important question for determining the angle, orientation angle, the forces, the angular rate, the curve as input as used as input for the vehicle autonomous systems. Using this kinematic model, we can obtain the state input and output system vectors. These equations are essential for multi-scale kernel principal component analysis to effectively model and estimate the variables of autonomous vehicles. This figure summarizes the input and output of the proposed techniques. The results of these techniques is two criteria SPU and T-square. Also, we used the pre-image of these techniques in order to obtain the estimated variables of our systems. Now let's describe the mathematical formulation of kernel principal component analysis. This technique requires both training and testing data, which are transformed in future space as shown in these equations. Also, we calculate the covariance matrix, the eigenvector, the orthonormal eigenvectors, which allows us to finally compute the Hotelling T-square and standard square prediction error SPU. However, this technique isn't very effective for nonlinear system and noisy data. To address this, we propose using multi-scale analysis and data reduction to remove noise. The data reduction is based on calculated distance as seen in the reduction equations. Additionally, the multi-scale is based on the wavelet function to handle different scales of data. This is the equation of variables after used wavelet functions. Also, this figure summarized our approach. This is the model of autonomous vehicles. The curvature as input. Also, use the measured data for multi-scale reduced kernel principal component analysis model. This technique gives the two criteria SPU and T-square. After that, we use a pre-image in order to obtain the X estimated. So this figure represents the variable of autonomous vehicles. This is the coordinates of position. Also, the velocity coordinates, the angular rate, and the orientation angle. So, to evaluate the performance of our approach, we used noise data as shown with signal noise rate. So we change this signal and we calculate the error, the mean square error MSU. There is this table summarized some results of each noise. So this table shows that the multi-scale kernel principal component analysis and multi-scale reduced kernel principal component analysis models outperform the nonlinear method. This improvement over nonlinear method is that integrate the multi-scale data and reduction raw data for effectively filter out noise while retaining the relevant characteristic of the raw data. Also, it can be stated that the performance of the multi-scale kernel principal analysis is enhanced through the optimization of kernel parameters. So some results of estimated variable of velocity and position, also angular rate and distinct day and orientation angle. These results shown that our approach technique, multi-scale reduced kernel principal component analysis model, are generally correctly estimated. So for this presentation, we have the modeling of autonomous vehicle based on data-driven technique kernel models. We evaluate the performance of this technique. We use it. We add some noise for data. Also, the significant reduction in the number of component analysis required for the reduced kernel principal component analysis highlighted the efficiency of these techniques. Then the performance of our models are further enhanced by integrate multi-scale with these models. Then the results underscore the potential of techniques as a very valuable tool in autonomous vehicle modeling, offering enhanced performance and computational efficiency. Further work could explore the application of multi-scale reduced kernel principal component analysis in real-world scenarios and further investigates its advantages in handling complex dynamics. Thank you for your attention.
Okay, unfortunately, we don't have the speaker here for questions or anything else. So I guess we'll go ahead with the next presentation. Last finish here, okay, good. Please. So the next presentation is entitled A Scalable Database Diagnostic Concept, Introduction and Application in Automotive Field. And it's going to be presented by Andreas Smits. Is that correct? Okay, by Andreas Smits. Very good. So the floor is yours.
Okay. Thank you very much for the possibility to present my work here. My paper was about the scalable database diagnostic concept and introduction and the application in automotive industry. So, okay. So today I want to talk about 4 points. First of all, I want to explain a bit the background of our research and the structure of the diagnostic concept. Then I will move on to the overview of the concept and the methods which are integrated in it. And then I will present the application, which is also in our paper. And in the end, I will show the outlook and further directions of research. So first of all, what was our idea about the scalable database concept? The idea or the doctoral research study was a counterbalanced database diagnostic, which is scalable and online as well as offline usable. So in the description, we have three-dimensional scalability. On the one hand, in regarding the measurement data and manifest or latent variables. Second, regarding the scalability measures, which I will explain in detail in the next slide. And then about the scalable diagnostic methods, you know, from the event before PCA, kernel PCA, or autoencoder. Our aim here is to have a multifunctional database diagnostic concept for mechatronical application, and especially in the automotive. And we want to evaluate different latent methods with some kind of header which is embedded in the concept. And it's in collaboration with the Technical University of Berlin and the IAV. The IAV is a company for automotive engineering. On the right side, you see our some kind of logo. It's a hypercube, which should explain a bit the latent space and the different ways to find the possible solution for the diagnostics. So here we see the 3 layers of the concept. The first layer is the pre-processing, where the data are read in and we can do unsupervised or supervised feature selection, and then do some standardization and transformation for the normal and faulty data. The next layer are the scalable measures, which are categorized in distribution measures and dependency measures. And here is the aim to provide an initial assessment of the data for the user of the concept. And in the last layer, we see the scalable diagnostic methods, which are principal component analysis, the kernelized version of it, and the autoencoder. And in each of these methods, we have different layers. So in the presentation today, I will focus on the fault detection, but in future papers we will also investigate the fault identification and isolation. So I move on to the overview of the diagnostic methods. So one special thing about these methods is that they are all latent projection methods, and they have similar internal structure. So they all try to find a reduced space. And in this draft of the new reconstruction feature space, we try to learn the dependencies between the variables. And this is one very important aspect to do the fault detection or to the fault diagnosis with these methods. So they all have similar fault detection indices and thresholds. So on the one hand, we use here the Hoteling's t-squared. We saw it in the presentation before, and also the squared prediction error. We use two kinds of thresholding. One is the chi-squared threshold, which is especially in the PCA and kernel PCA, and in the autoencoder, or especially in an alternative way, we use kernel density estimation to be independent from the assumption of the multivariate normal distribution. And in the end, the important ability of the three methods is the reconstruction ability. So we try to reconstruct the faulty data. And so we see in the residuals, for example, that we have a fault in the data or in our system. The similarities we see also here in the formulas. So we have in each of the column one method, and we see that in all of the three columns are the same fault detection indices. That is also one point in the diagnostic concept, that it's for the user equally to use. And we see in the thresholding, as said before, we have on the one side the chi-squared based thresholds, and on the other side the kernel density estimations. So now I want to show the application of the diagnostic concept in the automotive field. So first of all, we collect data from a real test vehicle. We split it in three different areas for starting the city driving, interurban driving, and highway driving. The background here is that we want to have a sample which is as comprehensive as possible. And we investigate two faults here. On the one hand, a defective intake temperature sensor in the motor of the car. And second one, which is the focus of this presentation, is the manipulation of the partial transmission pressure. So it's a dual clutch transmission, and we manipulate one of the transmission pressures with a negative drift. So first of all, we did the pre-processing in the first layer of the concept. So we resample the data and make an unsupervised feature selection with a variance threshold, so that all variables which have negligible variance are excluded. And then we transform the data to zero mean and unit variance. The scalability layer was the focus of one of our previous paper last year, and there we analyzed the data set regarding the measure of distribution and the measure of dependency. And in this presentation today, I will summarize both in the end, so that we have on the one side the results of the scalability measures, and on the other side the application of the diagnostic methods. So on this slide, we see the results. We see here some kind of new chart. It's a fault detection area chart on the right side. And we see 6 different colors. So for each of the methods, we see the different fault detection indices and some kind of unique threshold. The advantage here is that you can see directly which of the methods detect the faulty areas. one has to say here that we have an intermediate fault because of the transmission, and we see that only the kernel PCA and the autoencoder with the SPEs fault detection indices detect it right. So the t-squared on the other side has not so good results. So in the next slides we will focus on the SPE. To sum a bit up about the last paper and the scalability measures, we see here that we have used the measures of distribution. On the one side it was the multivariate skewness, and on the other side the multivariate kurtosis. For the dependency we use the Pearson correlation coefficient, which is very normal, and on the other side the distance correlation, which has the background to also detect nonlinear dependencies. Furthermore, we make a benchmark data set from a normal distribution, which is the same as our analyzed data set in the first and second moment of the multivariate normal distribution. And we can then show it the user in some kind of a radar chart, so that the user knows, okay, my data is very skewed or is very far away from the multivariate normal distribution. This is one important information, because we can say then, and this is also here in the boxes in the end, if the data is very far away from the multivariate normal distribution, the chi-squared threshold is not very good to approximate the data. So this means that we have more kernel density-based estimations, which is also the case in our study today. And on the other hand, we have seen that there are strong nonlinear measures in the data, and so this is one point to prefer the kernel PCA or the autoencoder. So we conclude here that if the dependencies are very nonlinear, so we use more the nonlinear methods like kernel PCA or autoencoder. So as a small outlook, we investigate mechatronical systems at the moment, but we also want to move on out of the automotive industry in the railway sector, and therefore we look for the vehicles and the infrastructure monitoring. Also, we want, as I said in the beginning, the analysis of the second layer, so we want to do the fault identification and isolation, which will come up in the next papers. And one further investigation should be a second iteration between the second and third layer of the concept, so that the user can skip to the measures again after he has seen one solution in the end. So that was my short presentation. I hope I was not too fast. Yes, and questions.
Thank you very much. Very good, thank you. We have time for some questions or comments or anything else. Anybody wants to ask or comment? I think it was an interesting presentation, and we appreciate it. What I missed a little bit was the physical significance of the actual data that you used, and especially the dynamics that are behind it. You mentioned about dependability, which I understand that it is related to dynamics, obviously, but you did not focus a little bit to give us some details about the dynamics. So the question is, what is your feature vector? Is your feature vector somehow related to the dynamics? Because the better the feature vector is related to the dynamics, then the better the chances will be that you will be able to do very good diagnostics.
Yes.
So do you want to comment maybe upon it? Or?
Yeah.
Okay, thank you.
Okay, I think it's twofolded. On the one side, it's in dependence of the data. So if the learning data have a good sample, so that the dynamics in it, I can learn better feature vectors. So in all of these methods, we try to learn some kind of feature mapping or feature space, where we try to reduce the dimension. Sure. And in this reduced dimension, we try to catch this dynamic between the correlations or the nonlinear behavior between the different variables. And I think in this case, the dynamics are embedded in this data, but for more time-based things, we have to change the threshold so that the threshold is not static, but also dynamic. So I think this would be one further step we could go, yeah.
Okay, well, thank you very much. I think it is important to try to select the initial features before reduction in the best possible way to represent dynamics that are sensitive to faults.
Yeah.
So maybe this is something that you could perhaps even think about even further in the future.
Yeah.
In my experience, at least, this is very important.
Yeah.
Okay. Okay, thank you. Any other questions or any comments before we move on to the last paper for the session? Thank you very much. So we move on to the last paper for today and for this session, certainly. It's entitled Fault Diagnosis and Identification in AGV Systems. And it's going to be presented by Annalisa Bertoli, correct? Right?
Yes.
Yes. So the floor is yours, and you can start.
Thank you very much for the presentation. I am Annalisa Bertoli, a PhD student from the University of Modena, Reggio Emilia. And today I'm going to present you this research. Maybe the last. Okay. First thing is to understand what is an AGV. And AGV is automated guided vehicles. They are widely used in an industrial feed to transport goods, materials, and in a controlled environment. Normally are used in automatic warehouse. And they can travel autonomously through a warehouse, and an onboard operator is not required. The AGV interacts with the surrounding environments. That will be the things that we are going to discuss in this presentation. And given a mission, AGV moves through predefined path, and it stops or slows down when there is an obstacle in the path, for safety reasons, obviously. The first thing, I make an example to understand how the AGV time works. Let's make an example that we have to do the path on the left. As you can imagine, the AGV has a speed for every section, and it is possible to predict the time planned that the AGV will use to do the mission. In reality, it's not as it seems, because it can occur that there is an obstacle, like an user, an operator. In this situation, the AGV slows down, or in this example, it stops and waits that the user moves away. And for this, it can happen with some obstacle that can be a physical object. So at the end, what it happens is that there is a loss in efficiency, because the time planned to do the mission and the real time that the AGV use to do the mission is different. Starting from that point, the research scope was to consider the relation with the environment and to understand how to intervene to decrease the loss in efficiency in an industrial plant. The methodology that we use is here described. The first thing to do is to default identification. The second two things to do is to identify the event that can cause default. Then the third thing is to identify the impact that every event has on the system. And at the end, we have to identify the variables that can help us to understand how to monitor the system. Otherwise, for us, it's very difficult to understand it. So in this situation, the fault, as I told before, is the losses in efficiency caused by the increase in average mission time because of an unnecessary stop or unexpected decrease in speed. Thanks to the expert of knowledge of experts in this field, we identified 3 possible situations that are most common. The first one is the insufficient number of reflectors, because the AGV moves and understands where it is using reflectors. So if we can see 3 reflectors at a time, it is not able to locate itself inside the plant. So 3 is the minimum number, but normally 4 is better. Then the warning state. In fact, it happens that the AGV goes in warning state and it decreases its speed automatically. The third thing to know is that in all the layout, the AGV knows the speed that it should have, but it happens in the real situation that this speed is lower. So we consider even this difference in speed. The event impact, as I told, the insufficient number of reflectors stops the AGV or decreases its speed. The warning state decreases its speed, and the difference between real speed and set speed causes a time loss in the system. The variables that we use are the number of reflectors, the warning state alarm, because the AGV knows if he is in a warning state or not, and the difference between the set speed and the real speed. I know this picture is not very clear, but it was the only one I have of the layout of the plant where I test the system, so you can see. No, probably you can't, but there are the wall and the warehouse inside. The first things I studied is the number of reflectors. What I did is that I collected the data for a long time. They are 45 days of data collected in a real environment. And then I check how many times the reflector was lower or equal to 3. And then, using an heat map, graphically I represent when these things happens inside the plant. As you can see, there is a green area in the middle that is where it happens more, because the value reported in the picture are a percentage value. To validate this analysis, I studied the destination node, because the AGV moves knowing its starting node and its end nodes. And I studied how many which destination node the AGV was reaching when the number of reflectors was lower or equal to 3. What I say is that this analysis give me the graph on the left, and the destination node 5 and 6 are in the green area. So this graph helped me to understand that the heat map was correct. The second analysis that I did is to locate the warning state, because I was able to collect the data in real time. So in real time, I was able to locate when the warning state was activated to AGV inside the plant. And the last things I did was to analyze the speed difference using the same analysis I did at the beginning for the number of reflectors. And as you can see, for the speed difference, there are more area inside the plant that are involved. It is even possible to mix these 3 analyses, so to understand when the warning state is active, the number of reflectors is lower or equal to 3, and the destination node set is the number 5, and it happens 711 times in 45 days. To conclude this presentation, this paper presents research that allows to collect data in an industrial environment, understand the system, understand the loss in efficiency, and maybe the most important thing is that it supports the operator in the decision-making process because the final user was able to understand what we were showing him that I show you today. Thank you very much.
Okay, thank you very much. Nice presentation. And any questions or comments? Anything you would like to ask? Okay, I just like to ask a brief question. Okay, what you designed and what you've implemented so far, it can be used for any number of vehicles moving in this space, or there are some limitations on?
No, you can use the same process with the other AGV to collect all together and to study all together and to see the interference between the different vehicles in the path.
Okay, good. So any numbers of vehicles can be studied. Obstacles can also be there in any fashion, right?
Yes.
There are no limitations in this respect.
No, it can be used with different obstacles and with the different vehicles.
Good. Very good. Okay, any comments or questions? If nothing else, I would like to congratulate you again. Thank you very much. And I would like to thank all the speakers and everybody present here today for this session. And with this, we conclude the session and enjoy the evening. And I hope to see you tomorrow. Thank you very much. Have a good evening.